Picture a journey into the absolute black, far beyond the warm light of the sun, where a spacecraft travels alone. There is no roar of engines, no brilliant plume of fire pushing it forward. Instead, it moves with a profound and total silence, a ghost gliding on an ocean of nothingness. Its power comes not from burning fuel, but from something almost magical. It harnesses the cold of space itself. This is not science fiction. This is the reality of deep space exploration, made possible by one of the most ingenious and quietly revolutionary technologies ever created, the radioisotope thermoelectric generator, or RTG. This is the story of that silent engine, the nuclear battery that became the key to unlocking the outer solar system and forever changing our place in the cosmos. For most of human history, our gaze at the distant planets was just that, a gaze. We could see them as points of light, but the gulf between us and them seemed insurmountable, not just in distance, but in power. How do you run a sophisticated scientific laboratory in a place where sunlight is a faint, useless trickle, weaker than a candle flame seen from miles away? Chemical rockets are fleeting, their fury spent in minutes. Solar panels become useless artifacts as you leave the inner solar system. There was a fundamental barrier, a wall of darkness that for generations confined our ambitions to brief, fleeting visits. To push through that wall required a radical rethinking of energy itself. It demanded a source that was compact, incredibly reliable, and utterly independent. A source that could endure for decades in the most hostile environment imaginable. The solution was found not in the fire of the sun, but in the gentle, persistent warmth of a rare atomic heart. This is the tale of that solution, a journey through the history, the breathtaking science, and the incredible missions powered by these cold engines. We will see how a technology born from the tensions of the Cold War was transformed into a tool of pure discovery, enabling us to turn the deepest, darkest reaches of space into a place of wonder and revelation. From the first pioneers carrying messages to the stars, to the Voyagers rewriting our textbooks on the giant planets, to the rovers tirelessly searching for life on Mars, the silent hum of the RTG has been the constant companion. This is the story of a technology that traded the dramatic but short-lived noise of rocketry for the profound, enduring whisper of longevity, a whisper that has, against all odds, revolutionized our reach into the universe. It is a story of human ingenuity at its finest, and it is a journey we are about to begin together. So we have this incredible desire to explore, to send our robotic eyes and ears to distant worlds. But ambition quickly runs into a brutal, unforgiving law of physics, the inverse square law. This isn't a complex idea, but its consequences are profound. Simply put, as you move away from the sun, the intensity of sunlight doesn't just drop, it plummets. Think of it like a single light bulb in a massive, dark room. Stand right next to it and you're brightly illuminated. Take 10 steps back and the light on you isn't just a little weaker, it's now only 100th as bright. Take another 10 steps and it becomes a 10,000th as bright. This is the reality for a spacecraft. At Mars, which is about 1.5 times farther from the sun than Earth, sunlight is already less than half as strong. This is challenging for solar panels but still manageable. We have rovers on Mars that use them, but venture out to Jupiter, which is over 5 times farther out than Earth, and the sunlight is a mere trickle, only about 1/27th of what we enjoy here. By the time you reach Pluto, over 30 times more distant, the sun is just a very bright star in a perpetually black sky, providing less than 1,000th of the light. At that point, a solar panel the size of a football field would struggle to power a single household light bulb. They become massive, fragile, and ultimately useless pieces of hardware. And what about the power we use to get there? Chemical rockets are magnificent for the initial burst, the violent, fiery push needed to break free from Earth's gravity. But that's all they are, a short, spectacular burst. Once that fuel is spent, it's gone. The spacecraft is on a ballistic trajectory, a cosmic cannonball. For a brief flyby past a planet, this can work. You aim, you fire, and you hope your instruments can grab as much data as possible in a few frantic hours as you zip by at tens of thousands of miles per hour. But that's no way to truly explore. You can't stop. You can't orbit a world for years, studying its weather, its moons, its magnetic fields. You get one hurried snapshot, and then your spacecraft, powerless and silent, continues on into the infinite dark. To do any meaningful science, to stay at a destination, a spacecraft needs electricity. It needs power to run its computers, to fire its thrusters for course corrections, to keep its instruments from freezing solid, and most importantly, to power its transmitter to send the precious data back to Earth across millions, even billions of miles. A chemical battery might last for a few hours or days, but a mission to the outer planets is a journey of decades. This created what engineers call a power barrier, an invisible wall in the solar system beyond which sustained exploration seemed impossible. For a long time, our reach was limited to those quick flybys. We got our first grainy, tantalizing glimpses of Jupiter and Saturn, but they left us with more questions than answers. The planets were no longer just points of light, but they remained distant, mysterious giants. We knew that to understand them, we needed to go there and stay. We needed a power source that was like a loyal companion for the long haul, something incredibly dense, so it wouldn't take up much mass, something incredibly reliable, with no moving parts to break over 20 or 30 years, and something completely self-contained, utterly independent of the distant sun. The solution wouldn't be found in harnessing fire, but in something far more subtle and enduring, the steady, patient warmth of a slowly decaying atom. So where did this idea of a nuclear battery actually come from? It might seem like a product of the space age, dreamed up by rocket scientists for interplanetary travel. But the true origins are more terrestrial and more tense. The spark for this technology was ignited not by the dream of exploration, but by the strategic necessities of the Cold War. In the late 1950s and early 60s, as the United States and the Soviet Union faced off, there was a critical need for remote, reliable power. Imagine a surveillance listening post buried deep in the Arctic, or a navigational beacon on a desolate island. These sites had to operate unattended for months or even years. Running power lines was impossible, and sending people to refuel diesel generators regularly was impractical and risky. Solar panels were too fragile and unreliable in harsh weather, and chemical batteries simply wouldn't last. The solution emerged from a surprising place: the atomic energy programs that had, until then, been focused on weapons and large-scale reactors. Scientists and engineers realized that the very process that made some materials dangerous, radioactive decay, could be harnessed for a peaceful, practical purpose. They began developing incredibly small, rugged nuclear generators. The principle was straightforward. Certain radioactive isotopes, like strontium-90 or plutonium-238, naturally decay, and in doing so, they release heat. A lot of heat, and this isn't a burst of heat like an explosion. It's a steady, predictable, and long-lasting warmth, like a pebble that has been left in the sun for 1,000 years and continues to glow. This was the key insight. You could take a small amount of this material, shield it safely, and use its constant heat to generate electricity. The program that brought this to life was called SNAP, which stood for Systems for Nuclear Auxiliary Power. The first successful units were SNAP-3 and SNAP-9A. These weren't for spacecraft initially. They were designed for satellites, specifically for military and spy satellites that needed guaranteed power regardless of their position in orbit, even when in the Earth's shadow. In 1961, a SNAP-3 unit powered the Transit-4, a navigation satellite, marking the first time a nuclear generator was used in space. It was a proof of concept that worked, but the real breakthrough was the specific choice of fuel. While early units used other isotopes, scientists quickly identified plutonium-238 as the ideal candidate. Unlike its cousin plutonium-239, which is used in nuclear weapons, plutonium-238 has special properties. It emits alpha particles, which are heavy and can be stopped by a simple layer of shielding, even by the casing of the generator itself. This makes it much safer to handle. More importantly, its half-life is about 88 years. This means that in 88 years, half of the material will have decayed, producing half the heat it did at the start. For a deep space mission that might last decades, this translates to a very gradual, very predictable decline in power, something engineers can plan for with incredible precision. This shift in thinking was monumental. A technology born from geopolitical tension was being repurposed for one of humanity's most peaceful and ambitious endeavors, the exploration of the cosmos. The same principles that kept a listening post warm in the Arctic could now keep a spacecraft's electronics from freezing solid in the void between Jupiter and Saturn. The steady heartbeat of a decaying atom, once used to listen for enemies, was now being tuned to listen to the universe itself. This peaceful technological revolution set the stage for everything that was to come, transforming a tool of suspicion into an instrument of discovery. It was the moment the cold engine found its purpose. So we have our solution in principle, a power source that uses the steady heat from radioactive decay. But the universe is full of radioactive elements, from the uranium in the ground to the potassium in a banana. Why is one specific isotope, plutonium-238, considered so uniquely perfect for this task? The answer lies in a combination of properties that make it almost as if it were designed by nature itself for deep space travel. Not all radioactive materials are created equal, and plutonium-238 stands apart in several critical ways. First, let's talk about safety. Radioactivity comes in different forms: alpha particles, beta particles, and gamma rays. Gamma rays are like highly penetrating light. They require thick, heavy shields of lead or concrete to stop them. Beta particles are faster electrons, which also need significant shielding, but plutonium-238 primarily decays by emitting alpha particles. Think of an alpha particle as a relatively large, heavy, and slow-moving cluster. It's essentially a helium nucleus. Because of its size and charge, it can be stopped by something as thin as a sheet of paper or, more importantly, by the metal casing of the generator itself. This makes handling and containing the material vastly simpler and safer. The radiation risk is almost entirely internal. You wouldn't want to inhale or ingest the plutonium dust. But as a solid, sealed fuel form, it presents a minimal external hazard, which is absolutely crucial when you're launching it on top of a rocket. The second, and perhaps most important, property is its half-life of 88 years. A half-life is the time it takes for half of the radioactive atoms in a sample to decay. This isn't an on-off switch, it's a gradual, predictable decline. An isotope with a very short half-life, like days or weeks, would be like a brilliant flashbulb, incredibly powerful for a moment, but then useless. An isotope with an extremely long half-life, like uranium-238, which has a half-life of over 4 billion years, decays so slowly that it produces only a tiny trickle of heat. Plutonium-238 sits in the Goldilocks zone. Its 88-year half-life means that at the start of a mission, it's producing a substantial amount of heat. After 10 years, a typical mission duration, it will still be producing about 92% of its original power. After 20 years, it's around 85%. This gentle decline is something mission planners can bank on. They know exactly how much power their spacecraft will have not just at launch, but decades into the future, allowing for long-term operational planning. It provides a warm glow, as one engineer described it, that can last for generations. Then there is the matter of pure energy density. The power of plutonium-238 is almost unimaginably concentrated. A single pellet of plutonium dioxide, about the size of a large grape, can generate enough heat to keep a room warm. This incredible energy density is what makes RTGs so compact and lightweight compared to the alternatives. To get the same amount of electrical power for decades from solar panels at Jupiter, you would need arrays larger than a tennis court, which are utterly impractical to build, launch, and deploy. The plutonium fuel core for a modern RTG weighs only a few kilograms, yet it provides the unwavering heartbeat for a billion-dollar mission. It's a power source that you can hold in your hands, yet it can run a sophisticated scientific laboratory for half a century. Finally, it's essential to distinguish this from a nuclear reactor. A reactor works on the principle of a chain reaction, where atoms are split apart fission in a controlled cascade, releasing enormous energy that must be carefully managed. It's a complex, active system with control rods and coolants. An RTG is the opposite. It is entirely passive. There is no chain reaction. The plutonium is simply decaying naturally, like a log burning in a fireplace, but a log that was set on fire millions of years ago and is still giving off a steady, dependable warmth. There are no moving parts to wear out, no controls to fail. This passivity is the bedrock of its legendary reliability. It just works silently and surely, year after year after year. So, plutonium-238 is more than just a fuel. It's the ideal heart for these cold engines. Its unique blend of safety, longevity, power density, and simplicity makes it the irreplaceable enabler of our farthest journeys into the dark. Now we have this incredible source of heat, this warm heart of plutonium-238 beating steadily inside its protective casing. But heat alone isn't enough to run a spacecraft. A computer, a radio transmitter, a scientific instrument, these things need electricity. So how do you take that raw, atomic warmth and transform it into the clean, usable electrical current that brings a machine to life? This is where the true magic happens, and it relies on a principle discovered nearly 2 centuries ago, long before the space age even began. The genius of the radioisotope thermoelectric generator isn't in complex machinery, it's in its profound simplicity. It uses a device called a thermocouple, and its operation is a beautiful piece of physics in action. Imagine 2 different types of metal, say, a strip of copper and a strip of constantan, a special copper-nickel alloy. Join them together at one end to form a loop. This simple junction is the heart of the thermocouple. Now, here's the crucial part. If you apply heat to that junction, something remarkable occurs. The heat energizes the electrons in the metals, but because the 2 metals are different, their electrons behave differently. One metal will hold onto its electrons more tightly than the other. This difference in behavior creates a tiny electrical pressure, a voltage that causes electrons to flow through the loop. It's a direct conversion of heat into electricity, with no generators, no turbines, no moving parts whatsoever. This phenomenon is known as the Seebeck effect, named after the German physicist Thomas Johann Seebeck, who discovered it in 1821. An RTG is essentially a sophisticated collection of many of these thermocouples, all working together. The design is elegantly straightforward. On one side, you have the radioisotope heat source, a glowing hot block of plutonium dioxide that can reach temperatures well over 1000 degrees Celsius. This is the hot side. Each thermocouple is physically connected to this heat source. On the other side, you have the cold of space. The thermocouples extend out to a set of metal fins which act like a radiator. In the near-perfect vacuum of space, there's no air to carry heat away through convection, so these fins radiate the waste heat away as infrared light, cooling the other end of the thermocouples. The temperature difference is staggering hundreds of degrees between the hot junction and the cold junction. It is this difference, this thermal gradient, that is the engine of the entire system. The greater the temperature difference, the stronger the flow of electricity. The frigid vacuum of space isn't an obstacle, it's an essential component of the machine. The RTG actively uses the deep cold of the cosmos as its heat sink, making the environment itself a part of the power generation process. The electrons flow steadily, driven by that relentless atomic heat on one end and the infinite cold sink on the other. This is why it's so perfectly suited for deep space. It doesn't just tolerate the cold, it depends on it. The absolute key to the RTG's legendary reliability is that this is a solid-state system. There are no pistons pumping, no fluids circulating, no bearings that can wear out or seize up after decades of operation. There is literally nothing to break. The thermocouples are solid pieces of metal and semiconductor material fused together. They are subject to the gradual effects of time, of course. The constant extreme heat can slowly degrade their efficiency over many years, which is part of the reason the electrical output of an RTG slowly declines. But there is no single point of failure. This passivity is its superpower. While a mechanical generator with thousands of parts might have a million things that could go wrong, an RTG has almost none. It simply sits there, silently turning the warmth of decay into the power of discovery, year after year, with a steadfastness that is almost alien in its perfection. This elegant marriage of atomic heat and 19th-century physics is what gives our robotic explorers their decades-long lifespans, allowing them to whisper their findings back to us across the unimaginable void. With the fundamental science now understood, the ideal properties of plutonium-238 and the elegant simplicity of the thermocouple, the challenge shifted from the theoretical to the practical. It was one thing to know that a nuclear battery could work in principle. It was another entirely to build a device that could survive the violent shaking of a rocket launch, the brutal radiation of the Van Allen belts, and the extreme temperature swings of space, all while operating flawlessly for years. This monumental task of turning concept into reliable reality fell to a program with a name that sounded like it was from a science fiction novel: SNAP, the Systems for Nuclear Auxiliary Power. Initiated in the late 1950s by the United States Atomic Energy Commission in collaboration with the Department of Defense and later NASA, the SNAP program was an ambitious umbrella for developing small, compact power sources for a variety of applications. It was divided into two main branches. SNAP reactor systems, often called SNAP-ers, were true miniature nuclear reactors that used uranium fission. But the branch that would truly change history was the SNAP radioisotope series. These were the passive heat-to-electricity devices we now know as RTGs. The goal was audacious: to create a power source so rugged and dependable it could be trusted to operate in places where no human could ever go to fix it. The first major success came with SNAP-3. This unit, about the size of a small pail, generated a modest 5 watts of electrical power, just enough to power a single string of old-fashioned Christmas tree lights. But its significance was monumental. On June 29, 1961, a SNAP-3 unit was launched aboard the Transit-4, a satellite, a Navy navigation spacecraft. This event marked the very first time a nuclear generator provided electrical power in space. For the mission planners, it wasn't just about the power, it was about the guarantee. Unlike solar panels, which would be useless when the satellite passed through Earth's shadow, the SNAP unit provided constant, unwavering power, ensuring the satellite signals were always reliable. It was a resounding proof of concept, demonstrating that the delicate physics of thermoelectrics could be engineered into a device tough enough for spaceflight. Building on this success, the program developed more powerful units. SNAP-9 was a particularly pivotal model. It was designed with a critical safety feature. It would only achieve a stable orbit or burn up completely upon re-entry, dispersing its fuel harmlessly in the upper atmosphere. This burn-up safety philosophy was a direct response to the understandable concerns about launching nuclear material. In April 1964, a SNAP-9 provided power for the Transit-5 BN-1 satellite. When the rocket's third stage failed, the satellite never achieved its intended orbit. Just as designed, the SNAP-9 generator re-entered the atmosphere and burned up high above the Indian Ocean, with its plutonium fuel vaporized and dispersed. While this might sound alarming, post-event analysis confirmed that the design worked as intended, preventing any large chunks of material from impacting Earth. This incident, rather than being a failure, actually validated the extensive safety engineering behind these devices, proving that even in a worst-case launch scenario, the risks could be managed. These early missions were the crucial nursery steps for the technology. They weren't headed for the glory of Jupiter or Saturn. They were circling Earth, doing the vital but unglamorous work of navigation and communication. But that was the point. Every successful orbit, every month of flawless operation, was building an unassailable track record. Engineers were gathering priceless data on how the thermocouples aged, how the materials held up under prolonged radiation exposure, and how the entire system behaved in the real environment of space. Each successful mission chipped away at the skepticism and built the confidence necessary for the next, much bolder leap. The SNAP program was the essential training ground, proving that these silent, atomic-powered engines were not just a laboratory curiosity, but a dependable tool. They were the foundational chapters in a story that was about to expand from Earth orbit to the very edges of our solar system, setting the stage for the iconic missions that would forever change our understanding of the cosmos. With the technology proven in Earth orbit by the SNAP program, the stage was set for a far more ambitious debut. The goal was no longer just to circle our own planet, but to break through the power barrier and venture into the unexplored realm of the giant planets. This monumental task fell to a pair of pioneers, Pioneer 10 and Pioneer 11. These were not the most complex spacecraft ever built, but they were the first, the trailblazers. And their mission profile presented an insurmountable challenge for solar power. To journey to Jupiter and beyond, they needed a power source that could operate far from the sun, and the only answer was the radioisotope thermoelectric generator. Each Pioneer spacecraft carried 4 SNAP-19 radioisotope thermoelectric generators, not for immense power, but for unwavering reliability. These units provided a steady 155 watts of electricity at launch, enough to run the spacecraft systems and its scientific instruments. But the power they provided was more than just electrical. It was the power of longevity, the guarantee that this tiny emissary from Earth could survive the multi-year journey and still have the strength to phone home from across 500 million miles. The success of Pioneer 10 was a series of breathtaking firsts. Launched in March 1972, it became the first spacecraft to travel through the asteroid belt, a region once feared to be a treacherous field of rocky debris that would destroy any probe attempting to pass through. Pioneer 10 emerged unscathed, proving the belt was largely empty space. Then, in December 1973, it reached its primary target, Jupiter. The images it sent back were primitive by today's standards, but they were revolutionary. For the first time, humanity saw the colossal planet up close, its swirling bands of cloud, its great red spot, a storm larger than Earth that had been raging for centuries. Pioneer 10 measured Jupiter's intense magnetic field, its radiation belts, and discovered that the planet is predominantly liquid. Having completed its mission at Jupiter, Pioneer 10 did something even more profound. It kept going. Using Jupiter's immense gravity as a slingshot, it was hurled outward at a speed that would eventually allow it to escape the solar system entirely. It became the first human-made object on a trajectory to interstellar space, a silent ambassador on an infinite journey. But a spacecraft on an eternal voyage into the unknown presented a tantalizing possibility. What if millions of years from now, it was ever found by an advanced extraterrestrial civilization? What message could we possibly send? This led to one of the most poetic and symbolic acts in the history of space exploration. Astronomer Carl Sagan and his colleague Frank Drake conceived the idea of a plaque, a physical message attached to the spacecraft itself. Designed by Sagan's then-wife, Linda Saltzman Sagan, the Pioneer plaque is a simple, elegant diagram etched onto a 6 by 9-inch gold anodized aluminum plate. It is a message in a bottle cast into the cosmic ocean. The plaque is a masterpiece of scientific communication. At its top is a schematic representation of the hyperfine transition of neutral hydrogen, the most common element in the universe, providing a universal standard of time and length. To the left is a map showing the position of our Sun relative to 14 pulsars, rapidly spinning neutron stars that emit incredibly regular radio pulses, and the center of the galaxy. This pulsar map acts as a cosmic address, pinpointing the location and even the time of the spacecraft's launch, as the rotation periods of these pulsars will change over millions of years. Most iconic, however, are the figures of a man and a woman drawn to scale in front of an outline of the Pioneer spacecraft itself. The man has his hand raised in a gesture of goodwill. This simple image was meant to convey our form, our scale, and our peaceful intentions. The plaque is a profound symbol of hope and curiosity, a testament to a species that, having just learned to leave its own planet, was already thinking on timescales of millions of years. And this message to the stars, this fragile piece of gold, was carried not on the brief flash of chemical rocketry, but on the steady, silent, and enduring power of its nuclear batteries. The RTGs were more than just an engine, they were the guarantor of the message. They ensured that the plaque wouldn't just be a piece of debris attached to a dead hulk, but an active artifact from a living civilization, launched by a species that had harnessed the atom not for destruction, but for the peaceful pursuit of knowledge. The success of Pioneer 10 paved the way for its twin, Pioneer 11, which performed an even more daring feat. After its own successful reconnaissance of Jupiter, Pioneer 11 used the giant planet's gravity to alter its course and fly onto Saturn, becoming the first spacecraft to visit that ringed world in 1979, returning the first close-up images of its spectacular rings and discovering new moons. Together, the Pioneer missions proved that the outer solar system was within our grasp, and they did so on the silent, reliable power of atomic decay, carrying with them a message of who we are, a message powered by the very atoms that make up the stars. If the Pioneer missions were the bold first steps into the darkness, then the Voyager program was the epic sprint that followed. Conceived in the mid-1960s, mission planners at NASA, a jet propulsion laboratory, realized a rare celestial alignment was about to occur. In the late 1970s, the giant outer planets Jupiter, Saturn, Uranus, and Neptune would arrange themselves in a graceful arc across the solar system. This configuration, which happens only once every 175 years, presented a once-in-a-generation opportunity. A single spacecraft could use the gravity of one planet to slingshot itself onto the next, a technique called gravity assist, creating a grand tour that would be impossible with conventional propulsion alone. The challenge, of course, was power. Such a tour would last not for years but for decades, taking the spacecraft into regions where sunlight is a pale memory. The mission demanded a power source of unparalleled endurance, and the answer was a bold commitment to radioisotope thermoelectric generator technology. Each Voyager spacecraft was equipped with 3 RTGs, housed in a boom extending from the main body, providing a robust 470 watts of electricity at launch. This was the lifeblood that would allow Voyager to not just survive the journey, but to thrive, to observe, and to communicate with an ambition never before attempted. Voyager 2, ironically, was launched first on August 20, 1977. Voyager 1 followed 2 weeks later on a faster trajectory. Their primary mission was a 2-planet tour, Jupiter and Saturn, but the spacecraft were built with immense redundancy and capability, loaded with a suite of 11 sophisticated scientific instruments, from cameras and spectrometers to magnetometers and cosmic ray detectors. All of this required power, and lots of it. The RTGs were the silent, beating heart of this entire enterprise. As the Voyagers sped away from the Sun, their power output began its slow, predictable decline, a curve that engineers had mapped out with precision before launch. They knew exactly how much power would be available at each planetary encounter, allowing them to meticulously plan every observation, every data collection sequence for years in advance. This predictability was the ultimate luxury in deep space exploration, a luxury made possible solely by the steady decay of plutonium. The rewards began to flood in almost immediately. When Voyager 1 reached Jupiter in March 1979, it didn't just take pictures, it revolutionized planetary science. The images revealed a world of astonishing complexity and violence. Jupiter's Great Red Spot was a churning hurricane of epic proportions. Its moon Io, a world about the size of our own moon, was discovered to be the most volcanically active body in the solar system, with plumes of sulfur and sulfur dioxide shooting hundreds of miles into space. This was a stunning discovery. No one had expected to find active volcanoes anywhere but Earth. The Voyagers revealed that Jupiter's rings were far more intricate than previously thought, and its magnetic field was a vast, dynamic bubble of charged particles. Then came Saturn in November 1980 for Voyager 1. The detailed views of its magnificent rings revealed thousands of individual ringlets, braids, and strange, spoke-like features that seemed to defy gravity. The flyby of Saturn's moon Titan revealed a thick, hazy atmosphere, a world with a chemistry that might resemble the early Earth, but the grand tour was not over. While Voyager 1's trajectory after Saturn sent it arcing out of the plane of the solar system, Voyager 2 was perfectly positioned to continue the journey. Its path, carefully calculated, used Saturn's gravity to fling it toward Uranus. This extended mission was a testament to confidence in the RTGs. No one knew if the spacecraft or its power source would still be functioning after another 4 years of travel. Yet, in January 1986, Voyager 2 arrived at Uranus, becoming the first and only spacecraft to visit that enigmatic, tilted ice giant. It discovered 10 new moons, a complex magnetic field, and found that the planet's atmosphere, while seemingly featureless from afar, held subtle bands of clouds. 2 years later, in August 1989, Voyager 2 completed the grand tour with its triumphant arrival at Neptune. The images were breathtaking. A world of deep, vivid blue, swept by the fastest winds in the solar system, exceeding 1,200 miles per hour. It discovered the Great Dark Spot, a massive storm system similar to Jupiter's, and revealed its moon Triton as a bizarre, frozen world with geysers of nitrogen gas erupting from its surface. Throughout this 12-year odyssey, the 3 RTGs on each Voyager spacecraft performed flawlessly. They provided the power for every camera image, every scientific measurement, every course correction, and most critically, for the 23-watt transmitter that had to beam that priceless data back to Earth across billions of miles. The faint signal, carrying postcards from the edge of the known world, was often weaker than the output of a standard refrigerator light bulb by the time it reached our planet. But it was there, it was clear, and it was continuous. The Voyager missions returned more data about the outer planets than had been accumulated in the entire previous history of astronomy. They transformed the giant planets from distant points of light into complex, dynamic worlds with their own families of diverse and active moons. This was not a brief glimpse, it was a comprehensive study, an endurance test that the RTGs passed with flying colors, proving beyond any doubt that nuclear power was the key to unlocking the deepest secrets of our solar system. Think about the incredible journey that data takes. A photograph of Neptune's swirling blue atmosphere captured by Voyager 2 begins as a stream of digital ones and zeros. That signal is then transmitted by a radio onboard the spacecraft, a transmitter powered by those steadfast RTGs. But the power of that signal is almost unimaginably weak. By the time it has traveled the nearly 3 billion miles back to Earth, the signal's strength has diminished to a level of about 20 billionths of a billionth of a watt. To put that into perspective, the energy collected by the antennas of the Deep Space Network from that signal over several hours is less than the energy required to make a single snowflake fall to the ground. Catching this whisper, this faint electronic sigh from the edge of the solar system, is one of the greatest technical achievements in human history, and it relies not just on the spacecraft's power, but on an entire global system of listeners, a system that itself, in some of its most critical locations, depends on the very same technology that powers the explorers. This global ear is called the Deep Space Network, or DSN. It is not a single telescope, but a coordinated array of gigantic radio antennas strategically placed around the world at 3 primary sites: Goldstone in California's Mojave Desert, Madrid in Spain, and Canberra in Australia. This geographical spread is crucial. As the Earth rotates, at least one of these complexes is always facing deep space, ensuring we never lose contact with our robotic envoys. The antennas themselves are monumental feats of engineering, with their massive dish diameters of 70 meters, about the size of a football field, turned on its edge. These dishes are incredibly sensitive, able to be pointed with the precision required to track a spacecraft moving at tens of thousands of miles per hour from a distance of billions of miles. But sensitivity is only half the battle. To hear the whisper, you must also shout back. The DSN doesn't just listen, it sends powerful commands to the spacecraft, instructions for course corrections, software updates, and new scientific observations. Generating the immense power needed for these outgoing signals, and for the ultra-sensitive receivers that listen for the replies, requires a reliable and constant source of electricity. And this is where the story of the RTG comes full circle in a beautifully symmetrical way. While the main DSN sites are connected to their respective national power grids, some of their most vital support equipment is located in extremely remote areas. Consider a relay station high on a mountain peak, or a facility in a secluded valley chosen for its radio quietness. Running miles of power lines to these locations is prohibitively expensive and vulnerable to disruption from events like earthquakes or wildfires. For these critical nodes in the global communications web, the solution has often been the same as for a spacecraft: a radioisotope thermoelectric generator. These terrestrial RTGs provide the unwavering, independent power needed to keep the amplifiers, receivers, and data links running 24 hours a day, 7 days a week, through any weather and any terrestrial power outage. They ensure that the chain of communication remains unbroken. So we have a profound technological partnership. A spacecraft like Voyager, powered by its RTGs, sends its faint signal. That signal is collected by a giant antenna, a facility whose remote critical components might also be powered by an RTG. The data is then relayed around the globe to the scientists waiting at mission control. It's a continuous loop of silent power. The same atomic heartbeat that gives life to the messenger billions of miles away also empowers the listener right here on Earth, guaranteeing that the precious stories of discovery can make it home. The RTG is not just the power for the journey, it is the enabler of the conversation. It ensures that the grand tour of the planets is not a series of lonely, silent flybys, but an ongoing dialogue across the solar system, a dialogue that has fundamentally rewritten our understanding of the cosmos we call home. While the Voyagers were rewriting the textbooks on the giant planets, another equally ambitious mission was taking on a challenge much closer to home, but in many ways just as hostile. The target was Mars, a world that had long captured our imagination, and the goal was nothing less than answering one of humanity's oldest questions: are we alone? The Viking program of the 1970s was designed to land sophisticated laboratories on the Martian surface with the explicit purpose of searching for signs of life. But Mars presented a power problem that was the exact opposite of the outer solar system. The issue wasn't a lack of sunlight. Mars is close enough to the sun that solar power is a viable option. The problem was the environment itself, a world of brutal extremes that would test any machine to its absolute limits. A Martian day, or sol, is only slightly longer than an Earth day, about 24 hours and 37 minutes. During the day, temperatures at the landing sites might reach a pleasant, almost Earth-like -20 degrees Celsius. But when the sun sets, the thin Martian atmosphere, which is about 1% as dense as Earth's, offers virtually no insulation. The heat radiates away into space with terrifying speed. Nighttime temperatures can plummet to -100 degrees Celsius, a deep freeze that can shatter metal and crack electronics. For a solar-powered vehicle, this creates an impossible cycle. You have energy during the day to work, but as soon as night falls, you need a significant amount of power just to survive, to run electrical heaters that keep your delicate instruments, your batteries, and your computer brains from freezing into useless bricks of ice. A lander dependent solely on the sun would have to spend almost all of its daytime energy recharging its batteries just to make it through the night, leaving very little power for the actual scientific mission, the search for life. And then there is the Martian dust, fine, abrasive dust that settles on solar panels, steadily reducing their efficiency with each passing day. A dust storm can coat the panels, potentially cutting off the power supply entirely and dooming the mission. The engineers at NASA knew that to have any real chance of success, the Viking landers needed a power source that was immune to the day-night cycle and indifferent to dust. The answer, once again, was the radioisotope thermoelectric generator. Each Viking lander was equipped with two SNAP 19 RTGs, similar to those used on the Pioneers but modified for a planetary surface. They were not the primary power source, that was a pair of solar panels. Instead, the RTGs played a far more subtle and critical role. They were the lander's life support system, its constant companion in the cold. Mounted in protective cages on the lander's deck, these nuclear batteries provided a continuous stream of electricity, but more importantly, they provided a steady, radiant heat. This waste heat from the plutonium's decay was a gift of survival. It meant that the lander's vital internal components were always kept above their minimum operating temperatures, even during the long, deadly Martian nights. The RTGs turned the lander from a machine that had to fight for its life every single night into a robust, all-weather scientific outpost. This reliability was the key that unlocked Viking's incredible scientific potential. Viking 1 touched down on the plains of Crys Planitia on July 20, 1976, followed by Viking 2 in Utopia Planitia that September. They were marvels of engineering, each equipped with a robotic arm to scoop soil samples, cameras for panoramic views, and most famously, a suite of 3 biology experiments designed to detect metabolic processes of microorganisms. These experiments were power-hungry and required precise, stable temperatures to function correctly. Because the landers weren't constantly on the brink of freezing, they could conduct these sensitive experiments night or day. The RTGs provided the stable thermal environment that the delicate chemistry of the life detection experiments demanded. The results from these experiments were complex and remain debated to this day, with most scientists concluding they likely detected unusual soil chemistry rather than biological activity. But the point is, they were able to conduct the search thoroughly and for far longer than anyone had dreamed. The true testament to the RTG's value came not during the prime mission, but in the years that followed. The Viking landers were designed to operate for 90 days, but powered by the unwavering combination of solar panels by day and nuclear warmth by night, they kept going. And going, Viking Lander 1 communicated with Earth for over 6 years, finally succumbing to a faulty command sent by a human operator. Viking Lander 2 operated for 3.5 years until its batteries failed. They far outlasted their solar-powered successors, like the Mars Pathfinder rover Sojourner, which lasted about 3 months, or the Phoenix Lander, which survived for 5. The Vikings became long-term weather stations and geology labs, documenting the Martian seasons, recording temperatures, and measuring wind speeds. Their longevity provided a continuous, multi-year dataset that would have been impossible without the sustaining heat of their RTGs. They proved that nuclear power wasn't just for the cold, dark depths of space. It was also the perfect technology for surviving the punishing thermal extremes on the surface of another world, transforming a short-term visit into a long-term residency and setting a new standard for what was possible in planetary exploration. While the Voyagers gave us breathtaking flybys of the giant planets, they were like tourists on a high-speed train, snapping pictures through the window. To truly understand a world as complex as Jupiter, you need to stay. You need to move into the neighborhood, observe the changing weather, get to know the family of moons, and study the environment over not just days but years. This was the monumental task of the Galileo mission, and it sent the spacecraft into the most hazardous environment ever faced by a robotic explorer. Jupiter is not just a planet, it is a miniature solar system in its own right, dominated by a magnetic field of almost unimaginable power. This magnetic field traps vast swarms of charged particles, creating radiation belts so intense they are millions of times more powerful than Earth's Van Allen belts. For any spacecraft, this is an electronic nightmare zone, a place where high-energy electrons can penetrate shielding, fry computer chips, and degrade solar panels with relentless efficiency. This radiation environment presented an impossible challenge for solar power. While sunlight at Jupiter is weak, it is technically still present. You could theoretically build enormous, fragile solar arrays to collect it. But those vast, delicate wings would act like giant sails in a hurricane of radiation. The constant bombardment would quickly damage the photovoltaic cells, causing their power output to plummet far faster than the natural decline from distance. They would become useless long before the mission could achieve its ambitious goals. There was simply no alternative. To survive and operate in the Jovian system, Galileo needed a power source that was compact, rugged, and immune to this radioactive onslaught. The answer, once again, was the radioisotope thermoelectric generator, but Galileo's design took the concept a step further. Instead of mounting the RTGs on an external boom, engineers placed the two generators in a unique position, shielded partially by the main body of the spacecraft itself. This wasn't just about generating power. It was about using the spacecraft's own structure as a fortress wall to protect its atomic heart from the very environment that made that heart essential. After a long and dramatic journey that included a flyby of Venus and 2 flybys of Earth to gain enough gravitational momentum, Galileo finally arrived at Jupiter on December 7, 1995. Its mission was twofold, and both parts were audacious. First, it was to release a small probe directly into the swirling, violent atmosphere of the gas giant. This probe had no power source of its own for the main mission. It was battery-powered, designed for a single, glorious hour of data transmission as it parachuted down into the unknown. But getting that data back to Earth was Galileo's job. The mothership had to be in exactly the right position, with its main antenna pointed perfectly, to receive the probe's faint signal and then relay it across 500 million miles. This required flawless timing and, most importantly, unwavering power from the RTGs to execute the complex maneuver. The probe's descent was a voyage into the unknown. It survived for 57 minutes, plunging 156 kilometers into the Jovian atmosphere, measuring wind speeds of over 400 miles per hour, and discovering that the atmosphere was much drier than expected, with far less water vapor than scientists had predicted. It was a brief but revolutionary glimpse beneath the cloud tops, and it was a success made possible by the reliable presence of the nuclear-powered orbiter standing by as a faithful relay station. With the probe's mission complete, Galileo began its own primary task, a long-term orbital tour of the Jovian system. This is where the RTGs truly proved their worth. Over the next 8 years, Galileo made 35 orbits around Jupiter, each one a carefully planned trajectory to fly past its major moons Io, Europa, Ganymede, and Callisto. The discoveries came in a flood, each one reshaping our understanding of these worlds. The most stunning revelations concerned the moons, which were transformed from frozen, cratered rocks into dynamic, active worlds. Io, which the Voyagers had discovered was volcanic, was revealed by Galileo to be in a state of constant, global upheaval. The spacecraft observed more than 150 active volcanoes, with plumes rising hundreds of kilometers above the surface and vast lava flows reshaping the landscape. The intense heat driving this activity comes from tidal forces, as Jupiter's immense gravity flexes and squeezes the moon like a ball of clay. But the most profound discovery of the entire mission, one that still drives exploration today, was about the moon Europa. From a distance, Europa is a cracked, icy shell. but Galileo's close-up observations and measurements of its magnetic field suggested something revolutionary lurking beneath the ice. The data strongly indicated the presence of a global, salty ocean, containing perhaps twice the volume of all Earth's oceans combined, locked under an icy crust estimated to be many kilometers thick. This was not a frozen, dead world. The interaction of this ocean with the rocky seafloor below, heated by the same tidal forces that melt Io's interior, could create hydrothermal vents and environments that on Earth are teeming with life independent of sunlight. Galileo's instruments detected a weak magnetic field around Europa that fluctuated in a way that was best explained by a layer of electrically conductive fluid, like salt water, sloshing beneath the surface. In one fell swoop, Europa went from a curiosity to the single most promising place in the solar system to search for extraterrestrial life. This discovery alone justified the entire mission and set the stage for future explorers. Throughout this epic tour, the RTGs performed flawlessly. The radiation was relentless, and it did take a toll on the spacecraft systems, causing numerous anomalies and glitches that the ingenious team on Earth had to work around. But the power never faltered. The steady decay of the plutonium-238 provided a predictable and dependable stream of electricity that allowed Galileo to keep its cameras snapping, its spectrometers analyzing, and its transmitter sending back a treasure trove of data until the very end of the mission in 2003. By placing a nuclear-powered laboratory in orbit around Jupiter for 8 years, the Galileo mission did more than just collect data. It revealed the Jovian system as a complex, interacting family of worlds, each with its own stunning story. It showed us that even in the cold, radiation-blasted reaches of the outer solar system, there could be environments with the potential for life, all seen through the unwavering, nuclear eyes of a truly resilient explorer. If Galileo's mission was a deep and hazardous reconnaissance of a single planetary system, then the Cassini-Huygens mission to Saturn was a full-scale residency, a decades-long opera of discovery that redefined a world and its celestial family. The ambition was staggering, not a flyby, not even a simple orbit, but a comprehensive, multi-year study of the entire Saturnian system. The planet, its iconic rings, and its astonishing collection of more than 60 moons. To achieve this, the spacecraft would need to be a behemoth of scientific capability, the size of a school bus and weighing nearly 6 tons, loaded with a sophisticated suite of 18 instruments. And every one of those instruments, every computer, every thruster, and the vital transmitter needed to send data across 1 billion miles of space, demanded immense and unwavering electrical power. In the realm of Saturn, 10 times farther from the Sun than Earth, solar panels were not just impractical, they were comically inadequate. They would have needed to be as large as a tennis court to generate even a fraction of the required energy. The mission had one viable option, and it was a powerful one: 3 advanced radioisotope thermoelectric generators, a nuclear power plant in miniature that would provide a steady 700 watts of electricity at the start of the mission. This power was the lifeblood of an endeavor that would stretch across 20 years, from its launch in 1997 to its dramatic conclusion in 2017. For 13 of those years, Cassini orbited Saturn itself, executing nearly 300 revolutions around the ringed planet. Each orbit was a carefully choreographed dance, using the gravity of Saturn's moons to adjust its path, allowing it to study the system from every conceivable angle. This incredible longevity, this ability to be present and observant through seasons and celestial events, was the direct gift of the RTGs. They provided the platform for a scientific symphony, each movement revealing a new wonder. The mission was a partnership, carrying the European Space Agency's Huygens probe, which was destined for a historic landing on the haze-shrouded moon Titan. But it was Cassini's relentless, nuclear-powered orbit that set the stage for the entire epic. One of the earliest and most profound discoveries concerned a small, icy moon named Enceladus. Before Cassini, Enceladus was just a bright, frozen speck about the size of England and of little scientific interest, but Cassini's instruments began to detect something strange about this tiny world. Its surface was unusually smooth in places, scarred by giant fissures now known as tiger stripes. Then, in 2005, the spacecraft's magnetometer sensed a disturbance in Saturn's magnetic field around Enceladus, hinting at an atmosphere. The mission team immediately commanded a closer flyby, and the images that came back left them in stunned silence. Plumes of icy material were erupting from the South Polar region, shooting hundreds of miles into space. It was an active cryovolcano, a geyser of water ice, organic molecules, and salts. Further analysis confirmed the unthinkable. These plumes were originating from a global, liquid water ocean trapped beneath the moon's icy crust, heated by the tidal forces of Saturn's gravity. Cassini even flew directly through the plumes, its onboard mass spectrometer tasting the spray and confirming the presence of the key ingredients for life: water, organic compounds, and a source of heat. Enceladus was transformed in an instant from a frozen curiosity into one of the most promising places in the entire solar system to search for life beyond Earth. A discovery that would have been impossible without the power to sustain a long-term, flexible orbital tour. While Enceladus was a surprise, the moon Titan was a primary target, a world larger than the planet Mercury, shrouded in a thick, orange haze that had hidden its surface from view since the dawn of astronomy. Cassini carried a radar instrument that could pierce that haze, and what it revealed was a landscape of breathtaking familiarity and profound alienness. Titan has rivers, lakes, and seas, but they are not filled with water. In the -180°C cold, the liquid is methane and ethane, hydrocarbons that exist as gases on Earth but flow as liquids on Titan. Cassini's radar mapped vast shorelines and detected waves on the surfaces of these alien seas, but the mission's nuclear power enabled an even more daring feat: the delivery of the Huygens probe. After a 7-year journey piggybacking on Cassini, Huygens was released on Christmas Day 2004. As it descended through Titan's thick atmosphere, Cassini acted as a crucial relay station. Its powerful transmitter and RTG provided energy, ensuring that every bit of data from the probe made it back to Earth. The images from Huygens showed a world of rounded, icy pebbles on a floodplain, evidence of flowing liquid under a hazy orange sky. It was the first and only landing on a world in the outer solar system, a triumphant moment made possible by the mothership's silent, dependable power. For over a decade, Cassini continued its survey, discovering new rings, witnessing giant storms erupt on Saturn, and studying the intricate gravitational interactions within the system. But all good things must come to an end, and the mission planners designed a finale worthy of the spacecraft's incredible legacy. Knowing that Cassini was running low on the thruster fuel needed to maintain its precise orbit, and determined to prevent the unthinkable, a future crash into and contamination of a pristine world like Enceladus or Titan, they conceived the grand finale. In its last year, Cassini was steered into a series of 22 daring dives between Saturn and its innermost rings, a region no spacecraft had ever ventured into. This required immense power for the thrusters and constant communication with Earth. During these final orbits, Cassini collected its most precious data, measuring the mass of the rings to determine their age and composition, and sampling the particles in the planet's upper atmosphere. Finally, on September 15, 2017, Cassini was commanded to make one last maneuver. It turned its antenna toward Earth for a final real-time transmission and dove into Saturn's atmosphere. For as long as its thrusters could keep the antenna pointed, it sent back data, a final whisper from the edge of oblivion, until the increasing pressure and heat vaporized the spacecraft. It was a controlled, purposeful death, a testament to responsible exploration. The entire 20-year saga, from the first glimpse of Saturn's rings to the final plunge, was a symphony conducted on nuclear power. The three RTGs provided the unwavering rhythm that allowed every movement of this epic discovery to be performed, proving that with a silent, steady heart, humanity could not only visit distant worlds, but could truly come to know them as dynamic, complex, and endlessly fascinating places. After the epic, long-term residencies of Cassini and Galileo, the next great leap in exploration required a different kind of mission altogether, one defined not by patience, but by pure, unadulterated speed. The target was Pluto, a world so distant and faint that even with the most powerful telescopes, it remained a blurry pixel of light. For decades, it was the last of the classical planets, a mysterious frontier waiting at the edge of the known solar system. But reaching it presented a unique and daunting challenge. A conventional orbital mission was out of the question. The amount of fuel required to slow down and enter orbit around Pluto after a multi-billion-mile journey would have made the spacecraft impossibly heavy and expensive. The only viable strategy was a high-speed flyby, a celestial reconnaissance mission where the spacecraft would have one chance, one brief window of hours, to capture as much data as possible as it screamed past at nearly 36,000 miles per hour. This approach placed immense constraints on the spacecraft's design, demanding it be incredibly lightweight, yet packed with sophisticated instruments. And for power, there was only one choice, but it had to be a very specific and modern incarnation of the RTG. The New Horizons spacecraft, a compact, piano-sized probe, was a masterpiece of minimalist engineering. Every gram counted. Unlike the Voyagers with their 3 RTGs or Cassini with its 3 powerful units, New Horizons carried just one. This wasn't the RTG of the 1970s. This was a modern marvel, a general-purpose heat source radioisotope thermoelectric generator, or repurposed RTG. Its design was refined over decades, offering the highest power-to-weight ratio ever achieved. At launch, it provided a modest 240 watts of electricity, about a quarter of what a modern microwave oven uses. But that was all New Horizons needed. This single, lightweight nuclear battery was the spacecraft's solitary heart, responsible for every single function, keeping the electronics warm in the deep freeze beyond Neptune, powering the computer brains, running the scientific instruments, and most critically, fueling the transmitter that would send the precious data home. The entire mission was a calculated gamble on efficiency and precision, and the RTG was the enabler of that gamble, providing just enough steady, dependable power for a focused burst of unprecedented discovery. The journey itself was a testament to this efficiency. Launched in January 2006, New Horizons was the fastest spacecraft ever to leave Earth, rocketing away on a trajectory that used a gravity assist from Jupiter to slingshot it toward the outer darkness. For 9 long years, it traveled through the silent void, its systems in a mostly dormant state to conserve power, its RTG providing just enough energy to maintain its course and keep its systems from freezing. The team on Earth conducted occasional check-ins, but for the most part, New Horizons was a lonely traveler, its atomic heart beating steadily as it crossed the orbit of Uranus, then Neptune. Finally, in the summer of 2015, the moment of truth arrived. As the spacecraft began its approach to Pluto, the mission team woke it up fully. and the single RTG seamlessly provided the increased power needed for the most complex observation sequence ever attempted by an interplanetary probe. What followed was a revolution in planetary science. As New Horizons sped toward its closest approach, the images that trickled back transformed Pluto from a fuzzy dot into a stunningly complex and active world. No one was prepared for what they saw. Instead of a dead, cratered ball of ice, Pluto revealed a breathtaking diversity of landscapes. Vast, heart-shaped nitrogen ice plains, named Sputnik Planitia, showed no impact craters, meaning the surface was geologically young, being resurfaced by processes that scientists are still working to understand. Towering mountain ranges of water ice, some as high as the Rockies, stood against a frozen horizon. Most astonishingly, there were signs of recent geological activity, including possible nitrogen ice glaciers flowing around the mountains. The data revealed a thin atmosphere of nitrogen and methane, and hints of a subsurface ocean of liquid water, much like those suspected on Europa and Enceladus. Pluto was not the primitive relic everyone expected. It was a dynamic, living world in its own right, a place that challenged our very definitions of what a planet could be. All of these discoveries were crammed into an intense 24-hour period around the closest approach. The spacecraft, operating on a pre-programmed sequence, was like a robotic paparazzi, its instruments snapping pictures, measuring compositions, and analyzing the atmosphere in a frantic, flawless ballet. It couldn't store all this data. It had to gather it now and send it later, and with its single, low-power transmitter, sending that treasure trove of information across 3 billion miles of space became a marathon that took over a year to complete. The RTG's role was now one of extreme endurance. It had to power the spacecraft's computer and transmitter for that entire duration, a slow, patient trickle of data that was the final, critical phase of the flyby. The success of New Horizons was a triumph of this minimalist nuclear power. It proved that even a small, single RTG could enable a mission of the highest scientific ambition, opening a new window into the most distant parts of our planetary system. But the story didn't end at Pluto. The same RTG that powered the flyby had enough life left for an encore. With Pluto receding in its rear-view mirrors, New Horizons was steered toward a new target, a small, mysterious Kuiper belt object named Arrokoth. On New Year's Day 2019, it performed the most distant flyby in history, revealing Arrokoth to be a pristine, contact binary object, a frozen relic from the dawn of the solar system. This extended mission, this journey into the uncharted territory of the Kuiper belt, is only possible because the steady decay of that plutonium heart continues to provide just enough power, more than a decade after launch, to keep the conversation alive, pushing the frontier of exploration ever further into the cosmic dark. The Martian landscape presents a unique set of challenges for any visitor, robotic or human. While sunlight is available, it is a fickle and unreliable resource. The planet is infamous for its global dust storms, events that can shroud the entire world in a tan haze for months, blocking out the sun and turning daytime into a dim twilight. Even without these epic storms, a fine, abrasive dust constantly settles on every surface. For a solar-powered rover, this dust is a slow death sentence. Each day, a little more dust accumulates on the solar panels, reducing their efficiency. Some missions, like the Spirit and Opportunity rovers, were occasionally saved by dust devils, Martian whirlwinds that would serendipitously clean their panels. But that was a matter of luck, not a dependable strategy for long-term survival. Furthermore, during the Martian winter, the sun hangs low in the sky for months, and the days are shorter, drastically reducing the amount of energy that can be harvested. A solar-powered rover must enter a kind of hibernation, powering down almost all of its systems to conserve its dwindling battery reserves just to stay alive through the night. It cannot drive, it cannot use its most power-hungry instruments, and its scientific mission essentially grinds to a halt for a significant portion of the Martian year. This cyclical dormancy severely limits the pace and scope of exploration. This is the fundamental limitation that the Curiosity and Perseverance rovers were designed to shatter. They are not just rovers, they are nuclear-powered field laboratories on wheels, and their independence stems from a single, revolutionary piece of technology, the multi-mission radioisotope thermoelectric generator, or MMRTG. This modern marvel of engineering is the direct descendant of the RTGs that powered the Voyagers and Vikings, but it has been refined for a new era of surface exploration. While its operating principle, converting the heat from decaying plutonium-238 into electricity via thermocouples, remains the same, the MMRTG is designed with unparalleled flexibility and robustness. It provides a continuous source of power regardless of the time of day, the season, or the amount of dust in the air. For Curiosity and Perseverance, every single Sol or Martian day is a workday. This constant power translates into an incredible freedom of action. While a solar-powered rover might have to carefully budget its activities, perhaps driving for an hour and then spending the rest of the day recharging, Curiosity and Perseverance can operate on a schedule dictated by science, not by energy constraints. They can drive long distances, then immediately use their robotic arms to examine interesting rocks. They can work through the bitterly cold Martian night, when temperatures plummet to -100 degrees Celsius. This is not just about mobility, it is about the quality and depth of the science they can perform. Both rovers are equipped with sophisticated onboard laboratories. Curiosity's mission, for example, centers on determining whether Mars ever had the environmental conditions suitable for microbial life. To do this, it carries an instrument suite called Sample Analysis at Mars, or SAM, which is essentially a miniature chemistry lab. SAM can vaporize powdered rock samples in tiny ovens and analyze the gases that are released, looking for organic molecules, the building blocks of life. This process is incredibly power-intensive and can take many hours, even days, to complete. A solar-powered rover simply could not support such an instrument. It would drain its batteries completely. But for Curiosity, powered by its MMRTG, running SAM is just another task on the itinerary. Perseverance takes this capability even further. Its primary mission is astrobiology, specifically the search for signs of past microbial life itself. It is equipped with a complex drill system that can extract core samples of rock and soil, samples about the size of a piece of classroom chalk. But Perseverance doesn't just analyze these samples on the spot. It is the first step in an ambitious campaign of sample return. The rover carefully seals these pristine samples in ultra-clean tubes and leaves them in a designated cache on the Martian surface for a future mission to collect and bring back to Earth. This entire process, from drilling to sealing and caching, requires immense precision and power. The drill alone uses a significant amount of electricity, and the robotic arm must operate with pinpoint accuracy. The MMRTG ensures that Perseverance has the steady, unwavering power needed for these delicate operations, regardless of the weather. It can drill during a dust storm, it can analyze a sample at 3 in the morning, and it can continue its search relentlessly, season after season. The MMRTG provides another, more subtle benefit beyond electricity: waste heat. The generator constantly radiates a significant amount of heat as a byproduct of its power generation. On a planet as cold as Mars, this waste product is a valuable resource. A network of fluid loops circulates this heat throughout the rover's body, keeping its sensitive electronics, computers, and instruments at a stable, warm temperature. A solar-powered rover must use its precious electrical energy to run heaters to avoid freezing to death at night, a massive drain on its limited resources. For curiosity and perseverance, this warmth is essentially free, coming from the same nuclear decay that powers their wheels and computers. This thermal stability is critical for the longevity of the rovers and the accuracy of their instruments, which often need to be kept within a specific temperature range to function correctly. The MMRTG, therefore, is not just a power source, it is a complete life support system, providing both the electrical and thermal energy needed to turn a machine into a resilient, all-weather explorer. This capability has allowed these rovers to become the longest-lasting, most productive surface missions in the history of Martian exploration, rewriting our understanding of the red planet's history and potential for life with every kilometer they traverse. Now that we've seen the MMRTG in action on the surface of Mars, let's peer inside this modern marvel to understand the engineering brilliance that makes such long-term reliability possible. The multi-mission radioisotope thermoelectric generator represents the culmination of decades of experience, a design refined for maximum flexibility and safety. Unlike its predecessors, which were often custom-built for specific spacecraft, the MMRTG is, as its name implies, a multi-mission power source. It's engineered to function equally well whether it's bolted to an orbiter hurtling through the vacuum of space or sitting on the dusty, cold surface of another world. This adaptability is a testament to its robust and intelligent design, which we can break down into 4 key components, each a masterpiece of materials science. At the very heart of the system lie the fuel pellets, the source of all its power. These aren't chunks of raw metal, but carefully crafted ceramic cylinders of plutonium dioxide. This ceramic form is chosen for its incredible stability and resistance to fragmentation. Imagine a material that can withstand immense heat and remain solid. That's what these pellets are. Each one is roughly the size of a large pencil eraser, but within that tiny volume is an immense concentration of potential energy. The plutonium-238 within is constantly decaying, and in the process, it heats each pellet to a glowing temperature of over 1,000 degrees Celsius. This is the warm heart of the entire system, and it must be contained with absolute security. This is where the second component comes into play, the General Purpose Heat Source, or GPHS modules. These are the ultimate protective shells for the volatile fuel. Each module is a layered fortress of advanced materials designed to survive the worst imaginable scenarios. Inside a graphite impact shell, which provides structural strength, sits a fine weave of carbon fibers that acts like a super strong basket, cradling the fuel pellets. The most critical layer is the cladding around each individual pellet, a capsule of iridium, one of the most corrosion-resistant and high-temperature metals on the periodic table. Iridium has a phenomenally high melting point and is incredibly strong. The entire purpose of this intricate, nested design is containment. It is engineered to survive not just the violent vibrations of a rocket launch, but also the catastrophic explosion of the rocket itself, a fiery re-entry into Earth's atmosphere, and even a high-speed impact with the ground or ocean. The GPHS modules ensure that even in a total mission failure, the plutonium fuel remains sealed away from the environment, a breathtaking commitment to safety that is built into the generator's very core. The next stage in the energy conversion process involves the component that gives the technology its name, the thermocouples. An MMRTG contains several dozen of these solid-state devices, which are the true magic that transforms raw heat into usable electricity. Modern thermocouples are far more advanced than the simple metal strips of early designs. They are made from sophisticated semiconductor materials, often based on lead and tellurium, which are significantly more efficient at converting a temperature difference into an electrical voltage. These thermocouples are arranged strategically so that one end is in direct contact with the searing heat of the GPHS modules, while the other end is connected to the outer casing of the generator. This setup creates the essential thermal gradient. The heat flows from the hot fuel through the thermocouples and must be dissipated into space. This is where the final critical component comes into play. The outer skin of the MMRTG is not a simple cylinder. It is covered in a series of sophisticated cooling fins. These fins are not just for show, they are a highly engineered radiator system. In the vacuum of space, there is no air to carry heat away through convection, so the only way to cool something down is through thermal radiation. The large surface area of these fins is specifically designed to maximize this radiative cooling. They glow with infrared light, efficiently dumping the waste heat from the cold end of the thermocouples into the cosmic void. This process is what maintains the vital temperature difference across the thermocouples. Without these fins actively radiating heat away, the entire system would eventually reach thermal equilibrium. The temperature gradient would collapse and the electrical generation would stop. The frigid environment of space is therefore not an enemy to be fought, but an active and essential partner in the power generation process. The MMRTG elegantly uses the cold of the universe itself to complete the circuit of energy conversion, a beautiful synergy between human engineering and the fundamental nature of deep space. Together, these four components, the fuel, the fortress-like heat source, the advanced thermocouples, and the radiating fins, form a closed, passive system of incredible elegance and resilience, a power source that truly lives up to its title as a modern marvel. The idea of launching any amount of plutonium into the atmosphere on top of a controlled explosion, which is essentially what a rocket launch is, rightfully gives anyone pause. It's a scenario that demands absolute certainty, where the word probably isn't good enough. The engineers tasked with making radioisotope thermoelectric generators safe understood this from the very beginning. Their goal wasn't just to build a power source, it was to build a fortress around that power source, a containment system so robust that it could withstand forces beyond imagination. The result is a masterpiece of defensive engineering, a series of protective shells designed with a single, non-negotiable purpose: to keep the plutonium fuel contained under any and all circumstances, even if the entire mission ends in catastrophic failure. This philosophy of safety begins with the fuel itself. The plutonium is not used in a pure metallic form. Instead, it is chemically bonded with oxygen to create a ceramic material called plutonium dioxide. This ceramic is incredibly stable and has an extremely high melting point. More importantly, it is manufactured into small, solid pellets that are very resistant to being broken up into fine, inhalable dust, which is the primary health concern with radioactive materials. Imagine the difference between a solid, dense brick and a pile of fine sand. If you were to strike the brick, it might chip, but it would not turn into a cloud of particles. The ceramic plutonium dioxide pellet is designed to behave like that brick, maintaining its structural integrity under immense stress. Each of these pellets is then given its first personal suit of armor. It is encapsulated within a shell of iridium metal. Iridium is a remarkable choice. It is one of the most corrosion-resistant elements known, and it has an exceptionally high melting point, even higher than platinum. This iridium cladding forms a primary barrier, a tiny, incredibly strong vault around each individual pellet. These encapsulated pellets are then stacked together inside a larger, cylindrical graphite container. Graphite is used here because it is another high-temperature material that is also very strong under impact, acting as a shock absorber. This entire assembly, the iridium-clad pellet inside its graphite shell, is known as a General-Purpose Heat Source Module, or GPHS module. Each module is a self-contained fortress for its radioactive fuel, but the engineering goes even further. Multiple GPHS modules are bundled together inside the main body of the radioisotope thermoelectric generator, which is itself built from strong, high-integrity metals and surrounded by layers of impact-absorbing material. This multi-layered approach is not accidental. It is a deliberate strategy called defense in depth. It means that if one layer of protection were to fail, the next layer is there to contain the material. The system is designed to be redundant and resilient from the inside out. Now, let's consider the worst-case scenarios this design is meant to survive. The first is a launch pad accident or an explosion during ascent. The radioisotope thermoelectric generator must be able to endure the immense overpressure and fragmentation of the rocket blowing apart. The rugged casing and the inherent strength of the GPHS modules are tested to ensure they can withstand this kind of violent detonation without rupturing. The second and perhaps most dramatic scenario is an uncontrolled re-entry. If a mission fails and the spacecraft falls back to Earth, it will slam into the atmosphere at tens of thousands of miles per hour. The friction with the air generates temperatures hotter than the surface of the Sun, enough to vaporize most metals. The radioisotope thermoelectric generator is designed to survive this inferno. The materials chosen, like iridium and graphite, are selected specifically for their ability to withstand these extreme temperatures. The shape of the heat source modules is also aerodynamic, allowing them to re-enter without tumbling uncontrollably, which would cause even greater heating. Finally, the system must survive the impact with the Earth's surface, whether that is land or ocean. The modules are built to hit the ground or water at high velocity and remain intact. The goal is to have the radioisotope thermoelectric generator, or at the very least its GPHS modules, sink to the bottom of the ocean or land in one piece where they can be recovered. The radioactive material remains sealed inside its multiple layers of protection, preventing any contamination of the environment. This incredible engineering was put to the test in a real-world event. In 1964, the Transit 5BN1 satellite failed to achieve orbit, and its SNAP-9, a radioisotope thermoelectric generator, re-entered the atmosphere as designed. While the unit burned up and dispersed its fuel at a high altitude over the Indian Ocean, the event confirmed the need for and led to the development of the even more robust containment systems used today. Every launch of a nuclear power source is governed by international treaties and rigorous safety reviews, and the meticulous design of these containment systems is the fundamental reason why, over dozens of missions spanning more than half a century, there has never been a release of radioactive material that has harmed a person or an ecosystem. It is a flawless safety record built on a foundation of breathtakingly thorough and cautious engineering. While NASA's pioneering work with radioisotope thermoelectric generators is the most well-known story, the pursuit of nuclear power for space exploration is truly a global endeavor. Recognizing the same fundamental limitations of solar energy in the outer solar system and on planetary surfaces, other major spacefaring nations have embarked on their own paths to develop this critical technology. This international interest underscores a universal truth in deep space exploration. To go far and to stay long, nuclear power is not just an option, it is a necessity. The journey beyond the inner planets demands a power source that defies darkness and cold, a challenge that has inspired a collective, worldwide effort to harness the atom for peaceful discovery. The most significant international player in this field is, without a doubt, the Soviet Union and later, the Russian space agency Roscosmos. While NASA focused on the peaceful exploration of the solar system, the Soviet program initially developed nuclear power sources for a different, yet equally challenging purpose, powering a series of navigational satellites known as the RORSAT program. RORSAT stood for Radar Ocean Reconnaissance Satellites, and their mission was to monitor ocean vessels, particularly naval fleets, from low Earth orbit. This required powerful radar systems, and solar panels were simply insufficient for the immense energy needs. The Soviet solution was the BES, or binary element system, a type of nuclear reactor that used uranium fission, a more complex and powerful system than the passive radioisotope thermoelectric generators used by NASA. These missions were high risk, and the world witnessed the consequences when one of them, Cosmos 954, malfunctioned in 1978 and re-entered the Earth's atmosphere, scattering radioactive debris over northern Canada. This event highlighted the dangers and led to significant redesigns. Beyond reactors, the Soviets also developed their own radioisotope thermoelectric generators for lunar and planetary missions. Their Lunar lunar rovers, the first remote-controlled vehicles to drive on another world, were famously powered by a polonium-210 radioisotope heater unit to survive the frigid lunar nights, a different but related application of nuclear materials to combat the cold of space. More recently, China has emerged as a major force in space exploration, and its ambitions extend far beyond Earth orbit. The China National Space Administration has made the development of nuclear power for space a key strategic priority. Their lunar exploration program, which includes the successful Chang 3 and Chang 4 landers on the near and far sides of the Moon, has relied on radioisotope thermoelectric generators to provide warmth during the 2-week-long lunar nights. These generators, developed indigenously by Chinese scientists, have been crucial for extending the operational life of the landers and their rovers, U-2 and U-22. But China's vision is even grander. They are actively developing much more powerful nuclear systems for future missions, including a proposed nuclear reactor that could power a permanent international lunar research station, a project they are developing in partnership with Russia. This station would require a continuous, robust power supply to support habitats and scientific experiments through the long lunar night, a capability that only nuclear fission can provide. Furthermore, China has its sights set on the outer planets, with conceptual plans for missions to Jupiter and its moons, voyages that would be impossible without the steady, sun-independent power of advanced radioisotope thermoelectric generators. China's rapid progress in this area signals a new chapter in the global story of nuclear space power. The European Space Agency, or ESA, represents a collaborative model of space exploration, and its approach to nuclear power reflects this. Rather than developing a full radioisotope thermoelectric generator system entirely on its own, ESA has historically partnered with NASA, most famously on the Cassini-Huygens mission. The Huygens probe that landed on Titan was a European achievement, but it was carried to Saturn by the American nuclear-powered Cassini orbiter. This successful partnership demonstrated the value of international collaboration, where each agency contributes its unique expertise. However, ESA is not content to be solely a passenger. Recognizing the strategic importance of having independent access to deep space, the agency has begun its own research and development programs into radioisotope power systems. European scientists and engineers are working on advanced thermoelectric materials and safety protocols, with the goal of creating a European radioisotope thermoelectric generator capability within the coming decades. This would empower ESA to lead its own ambitious missions to the outer solar system without relying on another nation's technology, ensuring that Europe has a seat at the table in the next great era of planetary exploration. This global landscape is not just about competition, it is increasingly about cooperation. The International Lunar Research Station proposed by China and Russia, for instance, has been presented as an open project for international participation. Similarly, NASA Artemis program, which aims to return humans to the Moon, involves a wide coalition of international partners, including ESA, the Canadian Space Agency, and the Japan Aerospace Exploration Agency. While the initial Artemis missions will use solar power, the plans for a sustained lunar base will inevitably require nuclear power for survival during the lunar night. This presents an opportunity for shared technology and knowledge, where the expertise gained by one nation can benefit all of humanity's efforts to become a multi-planetary species. The challenges of developing safe, reliable, and efficient nuclear power for space are so immense that they naturally encourage collaboration. The protocols for launching nuclear material, the shared safety standards, and the basic physics of surviving in a hostile environment are universal problems that benefit from a global pool of scientific talent. The story of nuclear power in space is therefore evolving from a series of national achievements into a truly international endeavor, a collective human project to ensure that our curiosity and our reach are no longer limited by the fading light of the sun. This remarkable technology, this silent engine that has powered our greatest voyages of discovery, relies on a fuel that is as rare as it is perfect. Plutonium-238 is not like coal or oil that we can simply dig out of the ground. It is an isotope that does not exist in meaningful quantities in nature. It is an artificial element, a product of human ingenuity, and for decades, the entire ambitious enterprise of deep space exploration rested on a finite and dwindling stockpile. The story of plutonium-238 production is a dramatic subplot in our space saga, one of scarcity, anxiety, and ultimately, a determined rescue mission here on Earth to ensure the journeys could continue. The primary source of this precious material for the United States was the Savannah River site, a nuclear complex in South Carolina. During the Cold War, the site produced plutonium-238 almost as a byproduct of its main mission, which was creating materials for nuclear weapons. When the Cold War ended, the reactors at Savannah River were shut down, and the production line for our spacefaring fuel went cold. For years, NASA was able to sustain its missions by carefully rationing the existing supply, scouring its inventory for every last gram, and even purchasing a small amount from Russia in the 1990s. But it was a classic case of drawing from a savings account with no new income. Every new mission, every rover sent to Mars, every probe planned for the outer planets meant another withdrawal. Scientists and engineers at NASA began to face a sobering reality. They had the blueprints for incredible spacecraft, the ambition to explore new worlds, but they were running out of the one thing that could power those dreams into reality. The silent engines were in danger of falling silent forever, not because of a failure of technology, but because of a shortage of fuel. The process of creating plutonium-238 is not simple. It cannot be manufactured in a standard chemical plant. It begins with a different element, neptunium-237, which is itself a man-made material. Neptunium-237 is placed inside a nuclear reactor where it is bombarded with neutrons. It absorbs a neutron, becoming neptunium-238, which then rapidly undergoes radioactive decay, transforming into plutonium-238. This is a slow, meticulous, and expensive process. The resulting plutonium-238 then has to be separated from the remaining neptunium and other radioactive isotopes, purified, and then converted into the sturdy, ceramic-like plutonium dioxide pellets that form the heart of the radioisotope thermoelectric generator. Each step requires specialized facilities, highly trained personnel, and an immense commitment to safety and security. For a long time, with no active production, the expertise and the industrial capability to perform this complex alchemy were fading away, just like the stockpile itself. The turning point came when the scientific community sounded the alarm. A report from the National Academies of Sciences in 2009 laid out the situation in stark terms, warning that the supply was critically low and that without a restart of production, future missions beyond Mars would be impossible after the 2020 teens. This was a call to action that resonated in the halls of Congress. Lawmakers from both parties, recognizing that American leadership in space exploration was at stake, began to allocate funding. The effort was a partnership between the Department of Energy, which oversees the nation's nuclear infrastructure, and NASA, which is the end user. The mission was clear: re-establish a domestic production capability for plutonium-238. The work restarted at two key Department of Energy laboratories, Oak Ridge National Laboratory in Tennessee and Idaho National Laboratory. Oak Ridge took on the crucial first step of producing the neptunium-237 feedstock. Then the campaign began in earnest. The initial goal was modest but vital: to demonstrate that the process could be successfully completed, creating a small but steady trickle of new fuel. Scientists and engineers had to essentially reinvent the process, adapting old techniques with modern technology and safety standards. It was painstaking work, with each milestone celebrated as a major victory. The first new batch of plutonium-238, amounting to just a few ounces, was produced at Oak Ridge in 2015. While a tiny amount compared to the needs of a full radioisotope thermoelectric generator, it was symbolically enormous. It was proof that the pipeline was unclogged, that the knowledge had not been lost, and that America was back in the business of forging the atoms that would power its future in space. Today, the production effort continues to ramp up. The ultimate goal is to produce an average of 1.5 kilograms of new plutonium-238 per year, enough to support a steady cadence of nuclear-powered missions for decades to come. This is not just about quantity, it is also about quality. The new fuel being produced is of exceptionally high purity, which translates into better performance and longer life for the radioisotope thermoelectric generators it will power. This concerted effort is a testament to long-term thinking. It is an investment in curiosity, an investment in discovery, an acknowledgement that our reach into the solar system is a national priority worth sustaining. The fuel that was once a relic of the Cold War is now being created for a purely peaceful purpose: to power our robotic eyes and ears as they journey to worlds we can only dream of visiting ourselves. This successful resumption of production means that the silent power story, the tale of the cold engines, is no longer threatened by a fuel crisis. The atomic heart that beats within our distant explorers will have a steady supply for the next generation of missions, ensuring that the whispers from the edge of the solar system will continue to find their way home. For all their legendary reliability, the radioisotope thermoelectric generators that have powered our greatest voyages have one fundamental limitation: they are not very efficient. The simple, solid-state magic of the thermocouple, while incredibly dependable, only converts a small fraction of the plutonium's immense heat into usable electricity, typically around 6 to 7%. The rest of that precious thermal energy is simply radiated away as waste heat into space. It's a bit like having a roaring fire, but only using the faint light of a single ember to read by, while the vast majority of the heat warms the empty air around you. This inherent inefficiency has placed a ceiling on the capabilities of our robotic explorers. As our scientific ambitions grow, the instruments we want to send become more sophisticated, more power-hungry. We dream of powerful ground-penetrating radar to map subsurface oceans, high-definition video cameras to capture dynamic processes on other worlds, and advanced communication lasers to send back torrents of data. These are not fantasies, they are the next logical steps in exploration, but they demand more electrical power than a traditional RTG can provide without becoming impractically large and heavy. The question then becomes, how do we squeeze more electricity from the same small, precious brick of plutonium-238? The answer may lie in a technology that is both centuries old and startlingly modern, the Stirling engine. The principle of the Stirling engine is a beautiful piece of classical physics. Invented by Reverend Robert Stirling in 1816, it is a type of heat engine that operates by the cyclic compression and expansion of a gas, usually helium or hydrogen, which is permanently sealed inside the system. Unlike an internal combustion engine that relies on explosions, a Stirling engine is an external combustion engine. This means the heat source is applied from the outside. In the context of space power, that heat source would be the same glowing hot general-purpose heat source module used in an RTG. The engine works through a simple, elegant cycle. The sealed gas is heated by the plutonium, causing it to expand. This expansion pushes a piston. As the piston moves, it forces the gas into a cooler region of the engine where it contracts. The piston then returns and the cycle repeats. This back and forth motion of the piston can be used to drive a linear alternator, much like the one in a car, but instead of being turned by a crankshaft, it moves in a straight line, directly generating alternating current electricity. This mechanical process is far more efficient at converting heat into motion, and thus into electricity, than the passive thermoelectric effect. Where a modern RTG might achieve 7% efficiency, a Stirling engine-based system, known as an Advanced Stirling Radioisotope Generator, or ASIG, has been demonstrated to reach efficiencies of over 25% and theoretically could go even higher. This is a quantum leap in performance. It means that from the same amount of plutonium fuel, you could generate 3 to 4 times more electrical power. Alternatively, you could achieve the same power level as a traditional RTG using only a quarter of the precious plutonium, dramatically extending the limited fuel supply for future missions. This efficiency isn't just a number on a spreadsheet, it is the key that unlocks a new era of exploration. A spacecraft powered by Stirling generators could run a suite of instruments that would be unthinkable today. It could power a small submarine probe to explore the liquid methane seas of Titan, or operate a powerful drill and laboratory on the surface of Mars without any constraints. Of course, this incredible boost in efficiency comes with a trade-off, and that trade-off is complexity. An RTG is the definition of simplicity, no moving parts, just silent, steadfast power. A Stirling engine, by its very nature, has moving parts, the pistons oscillating back and forth. For a technology that must operate flawlessly for decades in the vacuum of space, with no possibility of maintenance or repair, the introduction of moving parts is a significant engineering challenge. Engineers must overcome issues of wear and tear, lubrication in a zero-gravity environment, and the potential for a single point of failure that could doom a multi-billion-dollar mission. The solution to these challenges lies in a philosophy of elegant, robust design and meticulous testing. The moving parts in an advanced Stirling radioisotope generator are designed to move only minutely, with incredibly precise clearances, and they use Flexure bearings, specialized springs that allow the piston to move without conventional bearings that would require oil and eventually wear out. The entire system is designed to be hermetically sealed for life, with the internal gas never needing replenishment. Prototypes of these generators have been tested on Earth for the equivalent of many years of continuous operation, demonstrating remarkable longevity and reliability. The goal is to create a machine whose mechanical motion is so refined, so predictable, that it becomes as trustworthy as the solid-state thermocouple. The potential applications for this next-generation power source are as exciting as they are diverse. Imagine a network of landers distributed across the permanently shadowed craters of the lunar South Pole, where scientists believe vast deposits of water ice may lie. These regions are in perpetual darkness, making solar power impossible. A small, efficient advanced Stirling radioisotope generator could provide ample power for a rover to explore these cryptic landscapes, using its drills and analyzers to characterize the ice, a critical resource for future human habitation. Further out in the solar system, the moons Europa and Enceladus call for even more daring missions. A Stirling-powered Cryobot could be the ideal tool to melt through kilometers of surface ice to reach the hidden ocean below. Such a probe would need substantial power not only to melt its way down, but also to operate a full suite of scientific instruments in the alien water, searching for signs of life. The waste heat from the Stirling system could even be used strategically to aid the melting process, making the entire endeavor more efficient. For orbital missions, the higher power output would enable the use of ion thrusters for more efficient propulsion and powerful lasers for high-bandwidth communication, turning the slow trickle of data from the outer planets into a steady stream. The development of the advanced Stirling radioisotope generator represents a crucial evolution in our spacefaring toolkit, a shift from the silent, steady glow of the thermocouple to the gentle, efficient hum of a mechanical heart, a heartbeat that will power the next great leaps into the unknown. But our ambitions are no longer confined to robotic scouts. Humanity itself is preparing to return to the moon, not for flags and footprints, but to build a lasting presence. This new chapter, embodied by NASA Artemis program, presents a challenge far greater than any faced by the Apollo astronauts, surviving the lunar night. Unlike Earth, which rotates on its axis every 24 hours, the Moon takes a full 27.3 days to complete one rotation. This means a single lunar day, from one sunrise to the next, lasts for about 14 Earth days, followed by a night of equal and terrifying length. For 14 Earth days, the surface is bathed in continuous, unfiltered sunlight, with temperatures soaring to a blistering 120 degrees Celsius. But when the sun sets, the temperature doesn't just drop, it plummets. With no atmosphere to trap heat, the lunar surface radiates its energy directly into the void of space, and temperatures can crash to a bone-shattering negative 170 degrees Celsius, colder than the surface of Pluto. This is not a gentle cycle. It is a violent thermal pendulum that swings between a furnace and a deep freeze. For a short-term visit, like the Apollo missions which lasted only a few days and conveniently landed during the lunar morning, this extreme cycle was manageable. But for a permanent base, a true Artemis base camp designed for astronauts to live and work for weeks or months at a time, the 2-week-long night is an existential threat. Solar panels, which would work brilliantly during the long day, become utterly useless for 14 straight days. a base reliant solely on the sun would need to store an impossible amount of energy in batteries to survive the night batteries that would have to be massive, incredibly heavy to launch from Earth, and would degrade significantly over many cycles of charging and discharging. The power required isn't just for a few light bulbs, it's for life support. It's for heating the habitation modules to keep the crew from freezing, for circulating air, for recycling water, for running communications equipment, and for powering the scientific experiments that are the entire point of being there. A solar-dependent base would essentially have to hibernate through the night, with the crew in a minimal survival mode, unable to conduct meaningful exploration or research. This turns the lunar night from a period of opportunity into a protracted, dangerous siege. To truly live on the moon, to work through its entire cycle, we need a power source that is as immune to the darkness as it is to the cold. We need a source that provides unwavering, continuous power, day and night, summer and winter. In short, we need the same technology that has powered our most distant robotic explorers, the radioisotope thermoelectric generator. The application of RTGs on the moon, however, would be different from their use on a spacecraft. Here, their role expands from a simple power generator to an integrated life support system. A lunar habitat module could be equipped with a compact RTG, or more likely, a system of smaller radioisotope heater units, which are even simpler devices designed purely to provide warmth without generating electricity. These units will be placed strategically around the base's exterior or integrated into its structure. Their constant, radiant heat would create a thermal barrier, fighting back against the relentless cold of the lunar night and drastically reducing the amount of electrical energy the base would need to divert to heating. This is a crucial efficiency gain. It means the energy from solar panels or a larger central power system, perhaps even a small fission reactor, can be dedicated to active work, to running laboratories, operating rovers, and manufacturing resources from the lunar soil, rather than being wasted on the constant, desperate battle against the cold. The RTG becomes a silent, steadfast guardian, a nuclear hearth that keeps the home fires burning on an airless world. But the most exciting potential for nuclear power on the moon lies in the most challenging places, the permanently shadowed craters. At the moon's south pole, the site chosen for the Artemis landings, there are deep craters whose rims are so high that sunlight never, ever reaches their floors. These regions have been in perpetual darkness for billions of years, and because of this, they are among the coldest places in the entire solar system, with temperatures hovering just a few tens of degrees above absolute zero. Within these frigid traps, orbital missions have detected strong evidence of water ice, a resource of immense value. This ice can be mined and split into hydrogen and oxygen for rocket fuel, turning the moon into a cosmic gas station for missions to Mars and beyond. It can provide water for astronauts to drink and oxygen to breathe. These craters are, therefore, the key to a sustainable, enduring human presence beyond Earth. But how do you operate in a place that never sees the sun? Solar power is impossible. This is where RTGs and their advanced descendants become absolutely indispensable. A robotic rover or a stationary power station equipped with an RTG could be deployed into these abyssal darknesses. It would provide uninterrupted power for drills, analyzers, and processing equipment, allowing us to prospect for and characterize these water deposits without any concern for the day-night cycle. The rover could operate continuously for years, its nuclear heart utterly unfazed by the eternal night. For a future human outpost located on the crater's sunlit rim, a power beacon in the darkness below, perhaps using a Stirling generator for higher efficiency, could beam power via microwaves or lasers to the mining equipment working in the shadows, creating a continuous industrial operation. The return to the moon with Artemis is not a replay of Apollo. It is the beginning of a settlement, and settlements require infrastructure that is resilient, reliable, and independent of the whims of the environment. The same silent engines that gave us our first clear look at Pluto and revealed the oceans of Enceladus are now poised to play an equally vital role right on our celestial doorstep. They will be the keepers of the flame, the guarantors of warmth and power that will allow human beings to not just visit the moon, but to truly become a species that lives and works on another world. The technology born in the deep cold of interstellar space is now ready to help us conquer the deep cold of the lunar night, turning a former barrier into a new frontier. And so we arrive at perhaps the most thrilling frontier in all of planetary science, a realm that exists not on the surface of worlds, but hidden deep beneath their icy shells. For decades, we imagined life could only exist in the Goldilocks zone, that narrow band around a star where water could remain liquid on a planet's surface. But the silent, nuclear-powered missions of Galileo and Cassini shattered that paradigm. They revealed that the most promising habitats for life in our solar system are not planets basking in sunlight, but dark, frigid moons orbiting the giant planets, worlds like Jupiter's Europa and Saturn's Enceladus. These are not the dead, frozen orbs we once thought them to be. They are dynamic, active worlds that hide a breathtaking secret, vast, global oceans of liquid water, locked away under kilometers thick ceilings of ice. These subsurface seas contain more water than all of Earth's oceans combined, and they are kept liquid not by the warmth of the sun, but by the relentless gravitational tug of war with their parent planets. This tidal heating flexes and needs the moon's cores, providing a steady, internal source of energy. We now have compelling evidence that these oceans are in contact with rocky seafloors, creating the potential for hydrothermal vent systems, exactly the kind of environments where, on Earth, life thrives completely independent of sunlight. The implications are staggering. We may not need to travel to another star to find a second genesis of life. It could be swimming in the dark waters right here in our own celestial backyard. But confirming this possibility presents an engineering challenge of almost unimaginable difficulty. How do you explore an ocean that is sealed beneath a layer of ice as hard as granite, an ice shell that on Europa may be 10, 20, or even 30 kilometers thick? You cannot land a rover on the surface and simply drill. That would be like trying to tunnel through Mount Everest with a handheld power tool. The solution being conceived by scientists and engineers is as audacious as the goal itself: a nuclear-powered cryobot or ice-penetrating probe. This would be no ordinary spacecraft. Imagine a cylindrical vehicle, perhaps several meters long, designed not for flight through space but for descent through ice. Its mission would be to melt its way straight down, descending slowly and deliberately through the frozen crust to reach the liquid ocean hidden below. The journey could take months, even years, a slow, silent pilgrimage from the sterile surface to the potentially living abyss. And for such a journey, there is only one possible source of energy: the steady, intense heat of a radioisotope thermoelectric generator, or better yet, its more powerful successor, an advanced Stirling radioisotope generator. The cryobot would essentially use its own power source as a downward-facing torch. The heat from the radioisotope system would be directed to a melting head at the front of the probe. As it melts the ice directly in front of it, the water would flow around the sides of the vehicle and refreeze behind it, creating a seamless, liquid-filled tunnel that quickly seals shut. This refreezing is a critical feature, not a bug. It permanently seals the passage behind the probe, isolating the pristine ocean environment from any contamination from the surface. The Cryobot would trail behind it a thin, hair-like fiber optic cable, its only tether to the world above, through which it would send its priceless data back to a lander on the surface, which would then relay it to Earth. This entire process is a beautiful synergy of nuclear power and the environment. The very thing that makes the environment so hostile, the profound cold, is what makes the melting process so efficient. The ice acts as an infinite heat sink, allowing the probe to use its thermal energy with maximum effect. Once the Cryobot finally breaches the bottom of the ice shell and emerges into the ocean itself, the mission enters a second, even more dramatic phase. The probe could then release a companion, a fully autonomous underwater vehicle, a nuclear-powered submarine designed to explore the alien sea. This submersible would be the eyes and ears of humanity in this unexplored realm. It would need its own source of power, not for melting ice, but for propulsion, for scientific instruments, and for communication. It, too, would likely carry a small radioisotope power system, providing it with the endurance to roam this dark world for months or years, far outlasting any battery-powered vehicle. Imagine this submarine, a lonely robotic vessel, turning on its lights in the perpetual blackness. What would it see? It would navigate through waters that have been isolated from the rest of the universe for billions of years. Its sensors would analyze the chemistry of the water, searching for the complex organic molecules that are the precursors to life. It would map the underwater topography, looking for the telltale heat and mineral plumes of hydrothermal vents on the seafloor, oases of energy in the abyssal dark. The scientific payload of such a mission would be the most sophisticated ever built, a complete astrobiology laboratory packed into a torpedo-shaped hull. It would carry high-resolution cameras to capture any macroscopic life forms, though most scientists expect any life to be microbial. More importantly, it would have mass spectrometers to identify complex molecules, DNA sequencers to detect genetic material if it exists, and sensors to measure everything from salinity and temperature to redox potential, painting a complete picture of the ocean's habitability. The discovery of even simple microbial life in such an environment would be arguably the most significant finding in the history of science. It would prove that life is not a rare, flukish event unique to Earth, but a natural and perhaps common process in the universe. It would mean that the galaxy could be filled with life, not on the surfaces of Earth like planets, but in the hidden oceans of icy worlds orbiting countless stars. The challenges, of course, are immense. The pressure at the bottom of an ocean tens of kilometers deep would be crushing. The communications delay to Earth would be measured in hours, requiring the submersible to be highly autonomous, making its own decisions in real time. And above all, there is the paramount issue of planetary protection. We must be absolutely certain that we do not contaminate this potentially virgin ecosystem with earthly microbes that could hitch a ride on the probe, confusing our search for indigenous life or, worse, wiping it out. The Cryobot's design, with its self-sealing tunnel, is a key part of this strategy, but every component would need to be assembled in the cleanest rooms ever constructed, sterilized with methods far beyond what we use today. The dream of exploring the oceans of Europa and Enceladus is no longer science fiction. It is the logical, albeit immensely challenging, next step in the journey that began with the silent power of the first RTGs. These cold engines, which first gave us glimpses of these icy worlds from orbit, now hold the key to diving into their deepest mysteries, carrying our curiosity into the abyss on a warm, steady glow of atomic energy. The twin Voyager spacecraft, our current ambassadors to the galaxy, have given us an incredible yet fleeting glimpse of the interstellar medium. They cross the heliopause, the boundary where the sun's solar wind is halted by the pressure of the galactic environment, and in doing so, they became the first human-made objects to leave the protective bubble of the heliosphere. But their journey beyond is one of diminishing returns. Their power, supplied by those venerable radioisotope thermoelectric generators, is slowly but surely fading. Voyager 1's instruments are being shut down one by one, and within a few years, both spacecraft will fall silent, becoming inert monuments drifting endlessly among the stars. Their mission was never designed for a detailed study of interstellar space. It was a bonus, a triumphant encore after their grand tour of the planets. They are pioneers in the truest sense, but they are also scouts who only had the resources to send back a few postcards from the frontier. The data they have returned from the void is revolutionary, but it has also raised far more questions than it has answered. We now know the heliopause is a dynamic and complex region, a cosmic weather front where the influence of our star meets the galaxy. But to truly understand our place in the cosmos, we need to do more than just cross this boundary. We need to set up a laboratory there to stay and observe for years, even decades. This is the audacious goal of the next great mission concept, an interstellar probe. The vision for an interstellar probe is not merely to repeat the Voyager's feat, but to vastly exceed it in every conceivable way. Imagine a spacecraft designed from the ground up with one purpose: to travel faster and farther than any object before it, carrying a suite of modern instruments to conduct the first dedicated exploration of the interstellar environment. The scientific objectives are profound. This probe would measure the exact properties of the interstellar medium, the density, composition, and magnetic fields of the thin gas and dust that floats between the stars. It would look back to image the entire heliosphere from the outside, giving us a family portrait of our solar system's place in the galaxy, much like the famous pale blue dot image, but for our entire cosmic neighborhood. It could directly sample interstellar dust grains and measure cosmic rays unaffected by the sun's magnetic field, offering clues to the formation of stars and planets. And perhaps most intriguingly, it could use its unique vantage point to observe the universe in wavelengths of light that are filtered out by the heliosphere, opening a new window onto the cosmos. But to achieve any of this, the probe must be equipped to operate not for a decade, but for half a century or more. It needs to be a marathon runner of exceptional endurance, and that demands a power source with unparalleled longevity. This is where the legacy of the cold engines becomes the blueprint for the future. The mission lifespan of 50 years or more immediately eliminates solar power as an option. The spacecraft would quickly travel to distances where the sun is just another bright star. Chemical propulsion is only useful for the initial push away from Earth. The only viable solution lies once again in nuclear power, but it may take two possible forms, each with its own advantages. The first is a direct evolution of the technology we know and trust, an advanced radioisotope thermoelectric generator. However, for such a long mission, the gradual decline in power due to the 88-year half-life of plutonium-238 becomes a significant factor. Engineers would need to design a generator with a much higher initial power output to ensure that 50 years later, there is still enough electricity to run the most critical instruments and the transmitter. This could mean a larger radioisotope thermoelectric generator or the incorporation of more efficient conversion technologies, like the Stirling engines we discussed, which could provide more power from the same amount of fuel, extending the functional life of the mission. The second and even more powerful option is nuclear electric propulsion. This is a different concept altogether. Instead of a passive radioisotope thermoelectric generator, the spacecraft would carry a small, compact nuclear fission reactor. This reactor would generate a substantial amount of heat, which would be used to produce large quantities of electricity. This electricity would then power highly efficient ion thrusters. Ion thrusters work by electrically charging a gas, like xenon, and accelerating it to tremendous speeds to produce a gentle but continuous thrust. While the thrust is small, it can be maintained for years, gradually accelerating the spacecraft to velocities far greater than what is achievable with a brief chemical burn and a gravity assist. A probe with nuclear electric propulsion could potentially reach the heliopause in just 10 to 15 years, compared to the 35 it took Voyager 1. This speed is not just about bragging rights. It means the spacecraft arrives with a much larger portion of its operational life ahead of it, allowing for a long and productive primary mission in interstellar space. The reactor would also provide kilowatts of power, enough to run powerful instruments and even high-bandwidth optical communication lasers, enabling a torrent of data to flow back to Earth, transforming the trickle from Voyager into a fire hose of discovery. The challenges of such a mission are as immense as its potential rewards. The engineering must be flawless, as there will be no second chances and no repairs possible. The communication system must be incredibly sensitive to detect the probe's faint signal from hundreds of astronomical units away. And perhaps most dauntingly, we must plan for a mission that will outlive most of the scientists and engineers who design and launch it. It is an investment in the future, a gift to the next generation who will be the ones to receive the data and make the discoveries. This long-term perspective is what makes the interstellar probe so inspiring. It is a statement of faith in the future, a declaration that our curiosity extends not just to the planets next door, but to the vast galactic ocean in which our solar system floats. By harnessing the silent, steady power of the atom, we can build a vessel capable of sailing that ocean, carrying our questions into the void and waiting patiently for the answers to whisper back across the light years. Yet for all its profound benefits, the use of nuclear material in space has never been a simple, unquestioned decision. It exists at a complex intersection of scientific ambition, public safety, and deep-seated ethical concerns. The very word nuclear carries a heavy cultural weight, evoking images of devastating weapons and catastrophic accidents like Chernobyl or Fukushima. It is understandable, then, that the idea of launching this material on top of a rocket, a vehicle that can sometimes fail in spectacular and fiery ways, generates significant apprehension and debate. This is not a debate to be dismissed, but rather one that must be engaged with openly and honestly, for the responsible use of this technology is as important as the discoveries it enables. The conversation stretches back to the very beginning, in the 1960s and 70s, as NASA prepared to launch its first nuclear-powered missions. Public protests and legal challenges arose. Groups of scientists and citizens voiced valid concerns about the potential for a launch accident that could rupture the containment and disperse radioactive material into the Earth's atmosphere. The central fear was of contamination, of a worst-case scenario where a failed launch could turn a Florida coastline or any other downrange population center into a radioactive hazard zone. These fears were amplified by the tense backdrop of the Cold War, where nuclear technology was primarily associated with global annihilation. Advocates for the missions had to make a difficult case that the same atom that could power a weapon of war could also be harnessed as a precise and peaceful tool for discovery, and that it could be done with an almost absolute guarantee of safety. This imperative for safety led to the creation of some of the most rigorous engineering protocols and oversight committees in the history of exploration. Before any nuclear-powered spacecraft is even assembled, Its design undergoes years of review by multiple independent bodies, including NASA Office of Safety and Mission Assurance, the Department of Energy, and often an interagency Nuclear Safety Review Board. The mission must receive formal approval from the White House Office of Science and Technology Policy, and NASA must prepare a detailed environmental impact statement for public review. The philosophy governing these reviews is not about achieving an acceptable level of risk, but about demonstrating that the risk is effectively zero. The containment systems, as we've explored, are designed to survive not just a successful launch, but the most catastrophic failure imaginable, an explosion on the launch pad, a fiery re-entry, and a high-velocity impact with the ground or ocean. This is a standard of engineering redundancy that is unparalleled in almost any other field. The track record speaks for itself. Over more than 5 decades, the United States has launched over 40 radioisotope thermoelectric generators and heater units on various space missions. There has been only one incident where a unit was intentionally destroyed, the SNAP-9 in 1964, which burned up as designed high in the atmosphere. While this resulted in the global dispersion of its fuel, extensive monitoring showed that the radiation dose to any individual was a small fraction of what we receive from natural background sources in a year. Since the implementation of the modern general-purpose heat source design, there has been no release of radioactive material in any launch accident. This flawless record is not a matter of luck. It is the direct result of an uncompromising culture of safety that treats every gram of plutonium with the utmost respect and caution. Beyond the immediate risks of launch, there are broader environmental and ethical considerations. One concerns the act of sending nuclear material into space itself. Could we be contaminating pristine worlds? This question is addressed by the principle of planetary protection, an international guideline that aims to prevent biological contamination of celestial bodies. For missions to places like Mars or Europa, which may harbor conditions suitable for life, spacecraft are assembled in clean rooms and sterilized to eliminate any earthly microbes that might hitch a ride. The goal is to ensure that if we ever do find life elsewhere, we can be certain it is truly alien and not something we brought with us. A radioisotope thermoelectric generator, with its intense heat, is actually baked during launch to a temperature that would destroy any microorganisms on its surface, making it one of the cleanest components on the spacecraft. However, a more nuanced ethical question arises when we consider the end of a mission. For the Cassini spacecraft, the decision was made to deliberately plunge it into Saturn's atmosphere to eliminate any chance, however small, that it could one day crash into and contaminate a moon like Enceladus. This was a conscious act of planetary stewardship, a recognition that our responsibility extends beyond the success of the mission to the preservation of these new worlds for future study. It set a powerful precedent for how we must manage our technological presence in the solar system. The debate also touches on the allocation of resources and priorities. Critics sometimes argue that the immense cost and potential risk of nuclear-powered space missions could be better spent addressing problems here on Earth. This is a valid perspective that speaks to a fundamental question about the purpose of exploration. Proponents counter that the pursuit of knowledge is an intrinsic human drive that has, throughout history, yielded unexpected and profound benefits for society. The technology developed for space exploration has spawned countless spin-offs in medicine, computing, and materials science. More philosophically, they argue that understanding our place in the cosmos is a vital long-term investment for humanity, one that inspires new generations of scientists and engineers and provides a unifying, peaceful goal for our species. It is a balance between addressing immediate terrestrial needs and investing in a future that expands our horizons and deepens our understanding of the universe. Ultimately, the continued use of nuclear power in space hinges on maintaining public trust through transparent communication and demonstrable safety. It requires a continual dialogue, acknowledging the fears while clearly articulating the immense rewards. The cold engines that carry our dreams into the dark are not deployed lightly. They are the product of a solemn pact between science and society, a pact built on the unwavering commitment that the power of the atom will be used not for harm, but solely to illuminate the unknown. Behind every gram of plutonium-238 and every perfectly calibrated thermocouple lies a story not of autonomous machinery, but of human perseverance. The silent engines we send into the cosmos are not just products of equations and blueprints. They are the culmination of lifetimes of dedication from thousands of individuals whose names will never be famous, but whose collective genius is written across the solar system. Picture the physicist who spends decades studying the subtle properties of semiconductor materials, not for a faster computer chip, but to eke out one more percentage point of efficiency from a thermocouple that must function flawlessly for half a century. Imagine the materials scientist tasked with finding a metal that can withstand the heat of re-entry, who runs simulation after simulation to ensure an iridium cladding will hold under the most extreme conditions imaginable. These are not abstract challenges. They are puzzles solved in laboratories and clean rooms by people driven by an almost unimaginable patience and a profound commitment to getting it right, not just for today, but for the mission that will still be operating when their own grandchildren are adults. The culture that binds these unsung heroes together is one of meticulous, almost obsessive attention to detail. In most engineering projects, a failure can often be diagnosed and repaired. A faulty engine on a car can be replaced. A bug in a smartphone's software can be patched with an update. But for a radioisotope thermoelectric generator on its way to Saturn, there are no second chances. Every component, every weld, every electrical connection must be perfect from the moment of launch. This reality forges a unique mindset among the teams. They operate under the principle of, if you can't prove it's safe, it isn't. Every decision is peer-reviewed, every calculation is double and triple-checked. A technician assembling a general-purpose heat source module isn't just following instructions. They are performing a ritual of precision, aware that their steady hands are the final barrier between success and a potential catastrophe. This immense responsibility creates a quiet, sobering atmosphere in the assembly facilities, a far cry from the dramatic countdowns and launches the public sees. It is a world of hushed voices, white bunny suits, and the constant hum of machinery ensuring a sterile environment, where the goal is to create something so reliable that it can be forgotten about for decades, its silent operation the ultimate compliment to its creators. Perhaps the most poignant figures in this story are the mission planners and systems engineers, the ones who must think in timescales that stretch beyond a single human career. They are the architects of patience. When they design a power profile for a mission like Voyager or New Horizons, they are making decisions based on predictive models that extend 50 or 100 years into the future. They have to anticipate the gradual degradation of the thermocouples, the slow decline of the plutonium's heat output, and plan the spacecraft's entire scientific life around that gentle, inevitable curve. They are playing a cosmic game of chess, thinking dozens of moves ahead, conserving power for instruments that won't be used for another 20 years, all while knowing they will likely be retired long before their master plan reaches its final stages. Their legacy is not a single discovery, but the enabling of decades of discovery, a gift of time bestowed upon the scientists who will follow them. This long-term perspective is a remarkable act of faith, a belief in the future, and in the enduring value of the knowledge their creation will send back. And we cannot forget the safety experts, the men and women who serve as the conscience of the entire endeavor. Their job is to be the professional pessimists, to imagine every conceivable thing that could go wrong, and then ensure the design can withstand it. They are the ones who ask the uncomfortable questions. What if the rocket explodes on the launch pad? What if the spacecraft re-enters the atmosphere over a populated area? They run complex simulations of fiery explosions and high-velocity impacts, not out of morbid curiosity, but out of a deep-seated ethical duty to protect both the public and the planet. Their work ensures that the incredible benefits of exploration are never outweighed by an unacceptable risk. They are the guardians who allow the dreamers to reach for the stars, confident that the path is as safe as humanly possible. The flawless safety record of nuclear power in space is their monument, a testament to a career spent imagining the worst so that the best can happen. The human story of the silent power is also one of collaboration across generations. A young engineer today working on the power system for a future mission to Europa is building on knowledge passed down from mentors who worked on Cassini, who in turn learned from the pioneers of the Voyager program. It is a continuous chain of expertise, a living tradition of problem-solving where lessons learned from a minor anomaly on a mission 20 years ago are incorporated into the design of a new generator today. This is not a field driven by fleeting trends or quarterly profits. It is a patient, cumulative science where progress is measured in incremental gains in efficiency and safety over decades. The result is that every new spacecraft that launches carries with it the collective wisdom, the late nights, the moments of frustration and triumph of everyone who has ever worked on this technology since the days of the SNAP program. They may never see their names in a headline, but these engineers and scientists have etched their legacy into the history of our species. They are the quiet force behind the silent power, the human heart that beats within the cold engines, ensuring that our curiosity continues to light up the darkness for generations to come. Consider for a moment the solar system as we knew it just 50 years ago. The outer planets were little more than fuzzy disks in even the most powerful telescopes. Their moons were mere points of light, and the space beyond Neptune was an uncharted blank on the map, a realm of pure speculation. The transformation of our understanding from that point to today is nothing short of a scientific revolution, and at the heart of that revolution has been a constant, silent companion. The radioisotope thermoelectric generator has been more than just a piece of technology. It has been the great enabler, the key that unlocked the door to the outer darkness and allowed us to step through. The vast majority of the breathtaking discoveries we've made beyond the orbit of Mars, the revelations that have fundamentally rewritten our textbooks, have come from missions powered by these nuclear batteries. They have been the steadfast guardians of our curiosity, allowing us to not just glimpse, but to truly study worlds that were once beyond our reach. This revolution began with a shift from simple reconnaissance to deep, sustained observation. Before the era of nuclear power, our forays into the outer solar system were fleeting. A spacecraft would hurtle past a giant planet, its instruments frantically gathering data during a few precious hours of closest approach before it continued on its silent, powerless trajectory into the void. It was like trying to understand an entire continent from a single, blurry photograph taken from a speeding train. The pioneers and Voyagers changed that dynamic forever. With their RTGs providing unwavering power, these spacecraft could operate for years, their missions extending far beyond a brief flyby. Voyager 2's Grand Tour was the ultimate expression of this new capability. It didn't just snap a picture of Jupiter, it studied the planet's complex weather systems, mapped its intense magnetic field, and revealed its moons as individual, dynamic worlds. At Saturn, it didn't just confirm the existence of rings, it discovered their intricate structure of thousands of ringlets and braids, and then it did the unthinkable. It continued on to Uranus and Neptune, worlds so distant that sustained observation was once considered a fantasy. The data it returned didn't just add new facts, it forced us to completely rethink the nature of the ice giants and their place in the solar system. Perhaps the most profound shift in our perspective came from the realization that habitability, the potential for life, is not confined to a narrow, sun-drenched band around a star. This was a paradigm shattered by the cold engines. The Galileo mission, with its nuclear-powered endurance, was able to conduct a long-term study of the Jovian system that revealed the stunning geological activity of Io, and most importantly, the strong evidence for a global subsurface ocean on Europa. This single discovery transformed astrobiology. Suddenly, a world far outside the traditional Goldilocks zone, a frozen ball of ice, became one of the most promising places to look for life in the entire solar system. Cassini deepened this revolution at Saturn. The discovery of the water-rich plumes erupting from Enceladus was a landmark moment, a direct sampling of a subsurface ocean that contained the basic ingredients for life. These were not discoveries that could be made from a quick flyby. They required the patient, years-long orbital surveillance that only a nuclear power source could provide. The RTGs allowed these spacecraft to be present, to watch, to measure, and to witness the unexpected, turning points of light into complex worlds with hidden oceans and active geology. The revolution extended to the very edges of the planetary system. For decades, Pluto was a mystery, a pixelated world whose nature was the subject of guesswork. The New Horizons mission, powered by its single, efficient RTG, transformed that pixel into a planet. The images and data it sent back revealed a world of astonishing complexity: nitrogen ice plains, water ice mountains, and a possible subsurface ocean. Pluto was not the dead, primitive relic many had expected. It was a geologically active world that challenged our definitions and forced us to see the Kuiper Belt not as a junkyard of frozen leftovers, but as a region teeming with dynamic and diverse worlds. This was a discovery made possible by the ability to pack a sophisticated suite of instruments into a small, lightweight spacecraft and power them all the way to the solar system's frontier, a feat that would have been impossible with solar panels. Even on Mars, the influence of this nuclear-powered revolution has been profound. The Viking landers, with their RTG-assisted survival, demonstrated that long-term surface operations were possible, setting the stage for the modern era of exploration. The Curiosity and Perseverance rovers, with their MMRTG, have taken this to a new level. They are not limited by dust, by seasons, or by the setting of the sun. They are all-weather, all-season mobile laboratories capable of drilling into rocks, analyzing samples, and caching them for future return. Their endurance has allowed them to act as robotic field geologists, reading the history of Mars layer by layer and building a compelling case that the red planet was once a warmer, wetter world, potentially habitable for microbial life. The cold engines have turned Mars from a distant object of telescopic study into a world with a rich and complex history that we are now actively deciphering on the ground. The legacy of these silent engines, therefore, is not measured in watts or years, but in the fundamental transformation of our cosmic perspective. They have given us a detailed map of what was once a blank space on the chart. They have shown us that our solar system is a place of immense dynamism, where moons can have underground oceans, where planets can have storms that rage for centuries, and where small, icy worlds at the edge can rival the complexity of the planets closer to home. This is a legacy written in the data streams of Voyager, the orbital paths of Galileo and Cassini, the flyby of New Horizons, and the tireless tracks of the Martian rovers. Every new chapter in our understanding of the outer solar system bears the indelible signature of the radioisotope thermoelectric generator. It is the technology that turned the faint points of light in our telescopes into real places, with real landscapes, real weather, and real mysteries, forever expanding our sense of what is possible in the universe we call home. And so we arrive at the end of our journey, a story that began not with a fiery launch, but with a quiet, fundamental realization. The tale of the radioisotope thermoelectric generator is a narrative that defies our usual expectations of power and progress. In a world captivated by noise and spectacle, this is a technology of profound silence. It speaks not with the dramatic roar of a rocket engine, a sound that echoes for mere minutes, but with a steady, unwavering hum that resonates for decades. It is a story of quiet perseverance, a lesson in the power of consistency over cacophony, of endurance over explosion. This humble device, born from the heat of a decaying atom, has become the most reliable traveling companion our species has ever created for its voyages into the unknown. It is a testament to a specific kind of human ingenuity, one that values patience, foresight, and meticulous care above all else. The engineers who designed these cold engines were not just building for a mission. They were building for the ages, creating a legacy that would outlive their own careers and continue to whisper back to us from the edge of eternity. This legacy is written across the solar system in the data we have received and the images that have transformed points of light into worlds. From the first grainy pictures of Jupiter's swirling storms sent by Pioneer, to the breathtaking vistas of Pluto's heart-shaped plains from New Horizons, every single revelation from the dark, cold reaches of our celestial neighborhood has been carried on the back of this silent power. The RTG has been the enabler of a perspective shift as significant as the first telescope turned toward the heavens. It allowed us to move from being mere observers of the outer planets to becoming intimate students of their complex lives. We didn't just see Saturn's rings, we came to understand their intricate dynamics because Cassini could watch them for 13 years. We didn't just confirm Europa's ice, we deduced its hidden ocean because Galileo had the power to study its magnetic field in detail over countless orbits. This technology has allowed us to be present, to witness the changing of seasons on Mars and the erupting geysers on Enceladus, turning what would have been fleeting postcards into a rich, multi-volume history of our solar system. As we stand on the cusp of a new era of exploration, the legacy of these cold engines provides a foundation of unwavering confidence. The ambitious missions we now dream of sending a probe to swim in the subsurface ocean of Europa, establishing a permanent base in the shadowed craters of the Moon, or launching an interstellar probe on a century-long journey are not fantasies. They are logical next steps, and their feasibility rests squarely on the continued evolution of this proven technology. The steady heartbeat of plutonium-238, which has powered our robots for 50 years, is the same rhythm that will power our future. The lessons learned in building the rugged, fault-tolerant RTGs for Voyager are directly applicable to designing the even more advanced Stirling generators or compact fission reactors needed for tomorrow's explorers. This is not a technology we are hoping to invent. It is a technology we are continuously refining, a trusted tool that grows more capable with each passing mission. Ultimately, the story of the radioisotope thermoelectric generator is a story about light. It is about our species' relentless drive to push back the darkness, both literal and metaphorical. These cold engines are the torches we cast into the cosmic night, and by their persistent, gentle glow, they illuminate wonders we could never have imagined. They have shown us that warmth and life can exist in the most frigid of places, that dynamism thrives in the void, and that our curiosity is a force powerful enough to span the gulf between stars. The silent, steady hum of these generators is the sound of that curiosity made manifest. It is a promise that our quest for knowledge will not be extinguished by distance or time, that the light of discovery will continue to shine back to us, powered by the quiet, atomic fire of human ingenuity, for as long as we dare to look up and wonder what lies in the dark.